পিনটা ওকে, ঠিক আছে। তারপর কিছু করলে ইরেজ। ব্যাস। হুম হুম Start. Yeah. Welcome back. So this lecture would be divided into three parts. One is we'll have a recap because I thought there were many questions and we should take things a little bit slowly so that you understand. Then we will do the basic deep learning networks like CNN and RNN and try to understand their limitations. And from there, we'll go to the embedding part and try to go to attention and self-attention. Okay. So you see, I have listed 5 things which I picked up that perhaps from the last day's feedback that perhaps that needs to be discussed. So here I just want to tell you one thing before I start that I understand that everything will not be understood in the first pass. But try to understand the basic concepts, try to understand the intuition behind these architectures so that you can develop upon it, okay, and appreciate how things are moving. So again, a very simple thing, I think this is again core of all machine learning, that what is a loss function. So a loss function measures how far the model's predictions are from true level. So this is what is loss function. The optimizer uses, so there is some true level and there is some predicted level. And this is what the distance between true level and the predicted level is measured by the loss function. The optimizer uses the loss to update model parameters via backpropagation. So I will talk a little bit of backpropagation also. We talked last day, but there was a lot of questions, etc. So I will just talk about it. Okay. So what is a training loop? If you see in the training loop, there is a forward pass. We get the value, get the predicted value, which is y hat is the predicted value. Okay. So this is what we predict. Then you compute the loss y hat means the true level and the predicted value. Okay. And then you have a backprop gradient and accordingly you update the weights. Okay. So there are various weights for various networks. So we update the weights and this is how we repeat until loss. Okay. So there are various types of loss functions like MSE, okay, binary cross entropy, categorical cross entropy, etc., etc. Okay. So there are various sorts of loss functions. So I just let me give you a little bit of idea about the loss functions. Like you can have a mean squared error where it would can be for regression tasks. So this is y and this is y hat, and you do a square and summation of square. So it summation of square and the number of samples. This is number of samples. Okay. So in some cases also you can you make it 1 by 2n. Okay. In some cases you can make it 1 by 2n so that you have uh, so that you just can have this intuition. There will be some, you are doing a back propagation. So we will have a differentiation from here, 2 will come and this 2 will get struck out. I will talk about this, don't worry. Okay. So what happens, this is penalizing large errors more heavily because it is squared. So larger the error, the penalization is more. And good thing is always non-negative. So, and perfectly fit means MSE is equal to 0. And it is differentiable. So this is a differentiable function. If you see, this is a differentiable function. So this is a differentiable function and it works well with gradient descent. Okay. So just take this. So actual is 300K and predicted is uh, predicted is 280K. So you can have this and you will have this. Okay. Actual is 450K and predicted is, so you have something like this. Okay. So the MSE is basically the average of all this. Okay. And it penalizes the 50K the most. Okay. So this is mostly used in regression problems. I will come to another example where I will talk about where I will talk about uh, so where I will talk about back propagation. Okay. So during back propagation, I will talk about that. So another very important type of loss function is cross entropy. So cross entropy is, say you have a true level 0 and 1. Okay. You have a true level 0 and 1 and you have a predicted probability between 0 and 1, 0 and 1. Okay. So you have a true level which is 0 and 1 and you have a predicted probability which can be, say, 0.75. Okay. And you have a logarithm. So key property is use log to heavily penalize confident wrong predictions. So if you have confident wrong predictions, that will be penalized. So say if this is, say, 0 and this is, say, 0.95, then this will get hugely penalized. Okay. If this is, say, or just for mathematical sake, if this is 1 and this is, say, 0.002, that means you are confidently telling the opposite prediction, which will be penalized. Okay. So output layer uses sigmod. So ultimately output layer uses sigmod. I think I have talked about sigmod last class. What was sigmod doing? Sigmod is a function which takes things to 0 and 1, 0 and 1. So this is what sigmod does. Okay. So a perfect prediction would be that if this is 0 and sensitive to class imbalance. Okay. This is sensitive to class imbalance. So that we can talk later, but that is a different deal. So let us take this, see this. Okay. So spam is 1, predicted is 0.95. Then loss is very low. So because your is 1 and you are predicting 0.95, that means you are almost doing the right thing. So the loss is very low and you can calculate this loss very simply by using this formula. Okay. And wrong and confident. So that's what I was trying to say, that you have 1 and predicted is 0.05. So it is a spam, but you are telling no, it's not a spam, and you are very confident. So, and you are telling it with very high confidence that this is not spam. So it is 0.5, 0.05. So then you will have a very high loss. Okay. Immediately the system would push back and tell, see, this is very wrong, go back and correct your weights. So BCA, so binary cross entropy, punishes confident mistakes far more than timid ones. This drives the model to be both accurate and calibrated. So, see, there is one very important question, one very important thing in life also. Say you are making a mistake, okay, and you don't know you are making a mistake. That is much more dangerous than you are making a mistake and you have some idea that you are making a mistake, okay. So, this is the life lesson which exactly binary cross entropy catches. Okay, it catches an experience where you don't make a mistake just like that. Okay, fine. And then we can extend this binary cross entropy to categorical cross entropy. Okay, categorical cross entropy is something like this. So you have one if sample, so it's not binary was two class. Okay, binary was two class. Fine. Now this is multi-class. Okay. So say there are three classes: bird, dog, and cat. Fine. There are three classes. So now what is happening? YIC is equal to 1 if sample I belongs to class C. So see this, it can belong to only one class. There is one sample, so it can belong to one class. Means I am assuming that we are, these classes are distinct. Okay, it can belong to one class. Okay, sample can belong to just one class. Okay, and YIC hat YIC is the predicted probability for class C. Same thing, exactly. This is hat and this is class C, and C total number of class and summation C sum over all classes. Okay. So if it is 1, it can be 1 here and 0 other places, but this Y hat C may be 0.9 here, zero point 0.2 here, point something like that. Means I would say this, let us see this, because if we do a normalization, it is 0 0.7, 0 0.2, 0 0.1. Okay. So this is what key property is generalization of BCE, binary cross entropy, to k greater than 2 classes. Output layer uses softmax. Okay, so there is an output layer which uses softmax. I will not go to softmax, but softmax is something like e to the power x summation of e to the power x. Okay, for x for all class, x belonging to C. Okay, so this is all classes. So this is a normalization. So you get some value. Say initially you get a value of, from this CCE, you can get a value 7 to 1. Okay, something like this. You get a value from CCE 7 to 1. The softmax normalizes and makes the summation is equal to 1. Okay, and so this becomes 0.7, this becomes 0.2, and this becomes 1. And now you have true levels 1 and 0, and accordingly you do this calculation. Okay, accordingly you do this calculation. This Y hat is basically softmax Y hat. Okay, this Y hat is basically softmax Y hat. I will repeat once more just to get you give you an idea. So again, what is binary cross entropy? Binary cross entropy is penalizing people who are making predictions confidently. Okay, wrong predictions confidently. If you are making a wrong prediction confidently, you are penalized, and you are also penalized a little bit if you are making a right prediction but with not much confidence. Okay, so what does this help? How does this help? This helps in a way that when the prediction is there, also there can be a calibration. So I didn't you discuss the term calibration here. So calibration means that, say, so one of the hard problems of machine learning is, okay, so say machine tells that, say, sample 1 is class 1 with confidence 0.9, okay, and sample 2 also is class 2 with confidence 0.7, okay. So now the question is, which is more likely to be mistaken? Okay, which is more likely to be mistaken? If it is a calibrated system, then the second one is more likely to be mistaken. Okay, if it is a calibrated system, then the second one is more likely to be mistaken. But in many cases, machine learning systems are not calibrated, and it is seen many times that this is more likely to be mistaken than this. Okay. So this is one of the problems of machine learning and one of the well researched thing of machine learning. But binary cross entropy tunes that, regulates that, and tries to make it calibrated. Okay. So this is what is binary cross entropy doing. And then we have the categorical cross entropy, which is basically the generalization of binary cross entropy, which is basically a generalization of binary cross entropy. And what is happening? It will have one of the class as 1, others as 0, and it does, and when the output comes, it does a normalization. When the output comes, it does a normalization so that the predicted probabilities become, it is converted into a probability so that this sum is equal to 0. Okay, sum is equal to 1, sorry. So whatever the I made a mistake. So whatever the output from the machine is coming, that is converted to a softmax, and so that the sum is equal to 0. Okay, and then the same thing which we have done in binary cross entropy is done. Okay, so I guess I gave you a good idea about various types of three major type of loss function. There is the MSE, there is a binary cross entropy, and then there is a softmax. Okay, then there is a softmax which does for multi-class classification, and that is done through categorical cross entropy. Okay, so now the next question which comes is that where do we use the cross entropy thing? Okay, so where do we use the cross entropy thing, or where do we use the loss function? So, let me just take this thing, a small example of gradient descent. Okay, I think we took an example of gradient descent, but there was still questions that please do gradient descent even more. Okay, and so I will concentrate on one weight. So please concentrate on one weight, the W3. Please concentrate on one weight, W3, and we will see how this weight is updated. Okay, we will see how this weight is updated. Fine. So as you remember, I talked about this here. There will be a forward pass, there will be a computing loss, and there is a backprop gradient. Okay. So there are three things. Fine. So let me go to the forward pass. Okay. Let me go to the forward pass. So what is forward pass? See, concentrate on this. Okay. W1 into X is ZH1. Okay. And H1 is the latent parameter, which is a sigma of ZH1. Okay. So there is a linear thing, then there is a hmm, this function. Okay, there is this function which is called a, there is a this function, and then this is sigma Z1 is H1. Okay. And similarly, you can see that H2 Z2 is equal to W2X, and H2 is again this function ZH2. Okay, this function ZH2. And similarly, take this part y hat. This is combination of both of this. So z y hat is equal to y3 h1 and y4 h2. Okay, and y hat is equal to again this function z y hat. Sorry. So I hope you have now understood this is a sigmoid function. Okay. This is a sigmoid function. So again, once more. So W1, see the forward pass. Forward pass is very simple. Forward pass is very simple. What is happening? You have a linear operation. ZH1 is equal to W1X. Okay, first pass. And then H1 is basically a sigmoid of Z1. Okay, is a sigmoid of Z1. Okay, fine. Next, similarly, H2 is again first a linear function, then a sigmoid. Okay, no issue. First a linear function, then a sigmoid. And similarly, if you see a y hat, first a linear function combining these two, and then a sigmoid. Okay, and sigmoid, you know, this is the formula of the sigmoid. So with this, see the initial parameters, we take x is equal to 1, y is equal to 1. Learning rate is important. We'll see, because based upon learning rate, we update the weights. Okay, W1, W2, W3, W4. We have given 4 weights of Ws. Okay, no issue. So we have given 4 weights of W. Fine. So now, after this forward pass is done, we have, so this is going on. See, we have Z1, H1. Okay, all calculations are there, and the slides will be shared. But just to understand that we are doing this forward pass, and what is a forward pass? For each row, there is a linear operation and there is a sigmoid operation. Okay, we are all on the same page. There is a linear operation, there is a sigmoid operation, and you can calculate Z1 and H1 accordingly. Fine. So then you can also calculate Z2 and H2 accordingly. Okay, and you get these functions. And similarly, we will get Z3 and Y hat. So now we are with Y hat. Okay, so we are with Y hat, and we have come to the forward function. We have come to the end of forward function. So once we come to the end of forward functions, what needs to be done? So this is the predicted, and this is the target. So now let us use one loss. So we will use a MSC loss. Okay. So we can use a mean squared error. MSC means mean squared error, and we get this. Fine. And this becomes square. When you square this, this becomes this. Okay. So mean squared loss is this, and if you are, so you are getting the mean squared loss, just that, because this square is this and half is mean squared loss. As I have told that many times, you use the half with y minus y square for denoting mean squared loss. Okay, just before I have told you, and this is mean squared loss. So now we are set that we have finished the forward pass. So what will happen at the backward pass? In the backward pass, the weights will be adjusted. This is what happens in the backward pass. the weights will be adjusted. And why? If the forward pass, there are some things which are learnable, and learnable are the weights. If these weights have not learned enough, then what happens? If these weights have not learned enough, then what happens? It is far, far away from the target. And if it is far, far away of the target, then the task or the action we have to take is to adjust the weight. Fine. So once we are at the forward pass, let us just concentrate on W3 and how W3 is updated. So what will be the updated? So we have to update W3, the gradient it contributes in the loss. Okay. So we have to we have to put that in the negative, that this is what W3 has contributed in the gradient of L. Okay. And this is a learning rate. So now DL, now we introduce chain rule, that DL dy hat dz3 dz3 dw3. So these are three things which we have there. Okay. So DL dy hat dz3 dz3 dw3. Okay. So what is DL dy? Okay. DL was L was y minus y hat whole square half. This is L. So DL dy would be basically you do a simple differentiation and you get this. Okay. You get a simple differentiation and you get this. So I get DL dy hat is clear. So now we have to get dy hat dz and dz dw3. These are the two things you have to get. So now just remember this. Again, let me go to the next thing. So what is the relationship between z and y hat? What is the relationship between y hat and z? Basically, y hat is a sigmoid of z. This is what we have seen. See, this is what you have seen, that there was a linear function and a sigmoid function. This is how simply we went. I'll just go back and show you once more. I know this may be so this is what every case it happened. There was a linear function, there was a sigmoid function. See, there is a linear function, there is a sigmoid function. Okay. So this is very good. So now think that dy hat dz will be basically dy hat dz will be basically the sigma z z3, and we can show that this is this one. You can go back and see that how sigmoid differentiates. I am not doing that, but sigmoid differentiates give you y hat 1 minus y hat. Okay. So so then dl dz3, we have dl dz3 as, from the previous slide we have y minus y hat, and this slide we have y hat 1 minus y hat. Okay. So this is from here and this is from, sorry, and this is from here. Okay. This is the first part and this is the second part, and both of them are done together. Okay. Clear? So DL Z3 is done. So what is left? The left is dz3 dw3. Is that what is left? Let us see. dz3 dw3. This is what is left. So now let me go back and see this carefully. What is, this is z3. Let us say this is z3. So this is z3 w3 dot h1 w4 dot h2. Okay. See this carefully. Can you tell me what will be del Z3 del W3. So since we are doing a partial differentiation, sorry, so then this will become constant. So this goes, and here only H1 will stay. So this will be H1. Okay. So I hope these three things are clear. So then I am now with H1 here. Okay. And this gives me the entire value. So now I can use that very carefully here, that we have dl dy, everything I can use together. Okay, everything I can use together. The three values I can use together. And once I use these three values, see here, I am using these three values and I am getting a value, and accordingly I am actually adjusting the weights from 0.8 to 0.8. Okay. Once more. Again, to understand, because this is not only about back propagation, this is about understanding how things work. So always there is a linear and followed by a non-linear, okay, operations which we saw. Okay. So and linear and non-linear, we saw a sigmoid. This way the forward goes. The backward, thing we have seen, I am concentrating on just backward thing. I am just concentrating on W3. I am just concentrating on W3. So W3 means learning rate into DL DW3. And this is chain rule, where DL DW3 is broken down into DL dy hat, dz3, dz3 dw3. And each of them I have shown, this is H1 and this is written there, and this was y1 minus y, I think, something like that. So these three values I have got, and accordingly I can calculate the value of this and adjust the weight of W3. So this way things will go on. So then W3 to W2, W2 to W1, and this way the weights are adjusted, and you go on running the system again and again to get the weights. Okay. So means one thing you can understand, that there is a inherent sequence things, and it may take a long time. And so you will slowly realize that why GPU was so necessary to do this sort of things, and normal CPUs were not so efficient to do this type of operations. You will slowly realize. Okay. So I think I have made it clear. I think I have made it clear about how things are. Okay. The third thing I think I need to discuss is underfitting, good fitting and overfitting. I talked about this. There were questions. Let me think about this and talk about this a little more once. So what is underfitting? Underfitting is model is too simple, fails to capture data patterns. Okay. So now what is happening? Say, say model is too simple and fails to capture data pattern. So there is a very complicated line, and you want to capture the essence of this line through a straight line. Okay. But this model is too simple. This model is too simple. So then there will be always training error. No matter how you draw that straight line here, 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 means you can do all sorts of interesting things and try to fit the model, but the data, underlying data, has no relationship with the model you have. The underlying thing is much more complex than the data. So this is important, underfitting. That's why you have high training error. Training error also doesn't go down. Okay. And you have similarly high test validation error. And this should not never this would never decrease, means the error will never decrease if you begin to train even more. Okay, so even if you train more and more, that error would not decrease. It is like a little bit of, I think I will tell you this story which is told about many people, but it is told about Nasiruddin, Mullah Nasiruddin. He was told that he has lost a key and he was searching the key in the light. Okay, but the key was lost in the room in darkness. Okay, so no matter how much he searches and how much the light is there, he will not find the key. So this is what is underfitting. Okay, this is what is underfitting. The good fitting is it has both low training error and low test and validation error. So this is what is training error, validation error. This is what we want. But what is overfitting? What is overfitting is that you have very low training error and high test validation error. Okay. So this is something like that the thing is very complicated. You have a very complicated thing, but there are some noises. It's not so complicated as such. There are actually it is this, but because there are some noises, you are actually having you are trying to follow those noises. You are trying to follow those noises and you will have a very low training error. But when real life comes or when the test time comes, you see that there is a very high test validation error. Okay, so this is a simple, I will give you a simple example about this. This is a simple example is that a new person has joined a company. Okay, a new person has joined a company and he or she tries to understand the vibe of the company, and so she or he tries to follow everything what the senior is doing. Okay, of everything of the senior is doing and tries to adjust her or his actions according to that, and many of this may be just noise. The seniors are doing just noise, but he or she begins to follow. Okay, so then how to stop that? So that's why in company you have a welcome thing. Okay, you have a you have something, you have people who are given uh, they are during the initial days they are given training, they are given ideas that how things work. So that is what is regularization. So what would happen if that is not given? Okay, then what will happen? This person, this poor person will go in the company for 2 months, 3 months, 6 months, 8 months. After that, he or she will understand what is the exact way to behave or what is the exact way to go and how things work. And this person would then have a good training. So, what I am trying to say that overfitting can be fixed two ways. One is that you give a training, that you give a introduction, you give a introduction, and that is what is regularization. Or you leave the new person to the dogs and let him or her learn by himself. So overfitting will also go if you have a lot of data. So if lot of data comes, slowly the system may learn. So this is the two ways of seeing that how underfitting works and how overfitting works. Okay, so this is what is, again I have written carefully. Model assumptions are too rigid, cannot capture pattern, high error on both train and test, and like fitting a straight line through a curved data set. Here the model is too sensitive to training, captures noise as if it was signals, low train error, high test error. That's a new joinee is just following the seniors and doing whatever he or she is doing. Like a complex curve that passes through every part. Okay, you are trying to part. So then we are always looking for in real life also. If you think, we are always looking for sweet spot, the sweet spot, good fit, balance bias and variance by tuning hyperparameters, regularizing the model, and validating carefully on held out data sets. So the the new joinee continuously get feedback. Oh, so let us see now with this small group of seniors, how is he adjusting? So this is how you slowly have the sweet spot, monitored by a gap between training loss and validation loss. Okay. So just to tell that training loss low, validation loss high. Okay. This is overfitting, both losses high, both losses staying high is underfitting. And you have various sort of regularization. Dropout is another type of regularization. Early stopping is another type of regularization. More data, as I told, that ultimately, if it's overfitting, if the person is good, person will learn if there is more and more data. And then you have this cross validation. I have shown that robust estimate of true performance. Fine. So let us just have a quick summary. Have a quick summary that there are parameters. Last class you asked what is the difference between bias and regularization. They are parameters. Okay, they are learned. So I have y x plus b. This is a parameter because say you have a line, if I don't have B, it will always pass through the center. Okay. And I want it to pass through here or here and here. So this is what we adjust. And that is what is B. Okay. So B is a parameter. But we also have hyperparameters. What is hyperparameters? Which you as a user have to give. Like what should be the learning rate? How many layers do we need? Means is it doable with one layer or we have to give multiple layers? Okay. How many epochs we have to run? What is the batch size? So the goal is to actually best model architecture, while parameters goal is to minimize loss function. Okay. And as I have told, underfitting, good fitting, overfitting, this is what we have to always check, and this is the goal of having a good fit. So I hope this part is clear. So again I will tell you two three things in short. Underfitting, fitting a fitting a curve with a straight line. Overfitting, always following every small changes which are happening. Okay. Parameters, those which are learned during training so that you minimize loss function. Hyperparameters, those you give, the user give to have the best model architecture, maybe best learning or best fast training, etc. So this is what hyperparameters are. So finally, I think there was some issue with this evaluation matrix and there was some confusion with this confusion matrix. So I thought I will just repeat this. Okay. So confusion matrix is a very important thing for evaluation, and we evaluate a system based upon this confusion metric. Okay. And what is this confusion metric having? There is a true positive. If the system is predicting malignant, whether it is actually malignant. This is true positive. Okay. What is false positive? System has predicted malignant, but it is actually benign. Okay. What is false negative? System has predicted benign, but it is actually positive. And what is true negative? Both system and both system and actually it is not, it is benign. Okay. So this is what it is. Just one more thing, that what is precision? Precision means that when you are predicting correctly. So how much have you predicted? See, you have predicted true positive correctly and false positive wrongly. Okay. So prediction is true positive by true positive plus false positive. Okay. And what is recall? Recall is that how many actual malignant are there. This can be seen by true positive and false negative, and how many are you actually capturing is true positive. So recall is true positive plus false negative. Okay. So I guess this makes the hmm, hmm, this makes the recap good. I hope I have been able to answer many of your questions, bring things together. Okay. So if there are some other questions on this, or we can start the next part. There are two questions. Okay. I have to. Ah, my screen is still shared. Huh? No, my it's not coming there. It is my screen is coming. No, no, it has to be their screen, no? Can you stop the screen sharing? Can you stop the screen sharing at least and show myself? Huh? Huh. It's fine. I think this is fine. So, who are, yeah, so you are telling, I see this that BC it says perfect prediction implies BC is equal to 0. What will the model overfit if it is contrary to what uh, will that make the model overfit? That is your question is. No, perfect prediction does not mean the model will overfit. It's just stating that the ideal minimum of loss function, okay, binary. Hmm. Just sorry, there is uh, some issues which are coming up with the thing. Okay. So again, let me just take this question. Sorry about some mix up here. Huh? So BC, it says perfect prediction implies BC is equal to 0. This is what you are telling. So if BC is equal to 0, will it lead to model overfit? Okay. So this is not that. Perfect prediction does not mean the model will overfit. It's just stating that the ideal minimum of loss function. Okay. So binary cost entropy means 0 simply means the model assigns probability 1 to the correct class and 0 to the wrong ones. Okay. So overfitting, however, is about generalization. Okay, a model overfits when it achieves very low loss. See, this BC is very low during training, but it is very high during validation or training or testing. Okay, so it is not about BC becoming 0 during training. Yeah. So see, one thing you are telling is makes some sense that I'll reformulate your question and put it in this way. If I begin to see BC as 0, should I be alarmed? if the loss goes so low, should I be alarmed during training? Yes, you should be alarmed that if the loss becomes so low, you should be alarmed. There are other tests, that's why you have regularization, etc. But here, when we were talking about this, we were talking about that BC0 simply means that if there is a right prediction, it is predicted with probability 1, which is an unlikely case. I get your point. Maybe you have not expressed this correctly, but in a system you are saying loss has become 0. That is not a good thing. Okay, generally that is not a good thing. So, so the cost function can have very good question. Have multiple global minimas. How to make sure we have reached the lowest value of cost function? Okay, so you cannot generally. So there is two things, that if the uh, function is convex, then you can say that you have reached the global function. Otherwise, you cannot generally guarantee you have reached the absolute global minima, especially for deep neural network where the cost function is non-convex and has many local minima and saddle points. Okay. Instead, in practice, we aim for a good enough minima that generalizes well, not necessarily the lowest possible value. Gradient descent and its variant does that. Gradient descent is a hill climbing thing. Okay, so it helps navigate the landscape, and techniques like random initialization, multiple restarts, learning rate scheduling, and momentum improve the chance of finding a better minima. So that all this gradient descent tries to escape minima also, so that you don't get stuck in a global minima. So importantly, we don't judge success purely by lowest training cost. Instead, we also see the validation loss. So this is important. I think again and again, what is validation? I told last class, let me repeat once more. So you have a training loss, okay, but you have a held out data set where you are not training it. So with that held out data set, you again check whether the loss has got minimum or not, got minimum or not. And as soon as it got validation loss gets minimum, otherwise you again do that training. So this validation loss checking and then going back to training is a process, and I talked about it last class. So the question is that it is not only validation loss, it is not only training loss, the validation loss has to be low and stable. We assume we have reached a good solution. So at least we have reached a good solution. We may not we have reached the best solution, but we have reached a good solution because there is stability. There is not changing. For small changes it is not changing. Okay, so there is some sort of robustness. So now, but in convex problems, as I have told in the beginning, the cost function has a single global minima, so gradient descent will reach it. But in deep learning, the goal is robust generalization rather than exact optimality. So remember this, we want robustness, robust generalization rather than exact optimality, because that is not possible. Means we would be happy to have exact optimality. Nobody is against exact optimality, but we want robust generalization. Okay, thank you. Okay, so then no, I think I can continue for some time. Hmm. So I hope those who are listening are not getting tired. I am not getting tired, so I hope those who are listening are not getting tired even. Okay. So I don't know. Okay. So we start. Huh. Okay. Oh, so there is another question. Okay. So yeah. Okay. Narayan Singh. Narayan Sen. Okay. We are unmuting Narayan Sen, and if he has some question, please ask.
No, I think. Am I audible?
Yeah. Please go ahead.
Okay. I think you answered my question. My question was actually you were saying that BC zero implied perfect prediction.
Huh.
However, my question was the slide before that we were saying that we will do the back propagation regularly until and unless we are tending to a kind of the loss gets minimized, right? That was the
Uh-huh.
basic perspective. So my question, and then I had asked a question that does that mean that every time we are training a model, we should
Uh,
keep on doing this back propagation until and unless we make it zero? To which I
no.
got an answer stating that
Yeah.
no, it might overfit or underfit. So
Huh.
the question was in perspective of that
Yeah. I understood your because
whether
I
for
understood
BC,
that
on one hand, we are
uh,
saying that if
that
it is
was
zero, it's
the
the perfect prediction. But on the other hand, we might say that that might not be the exact thing to look for. So I got my answer when you said that the
uh,
validation errors probably needs to be looked upon as. So it's
uh,
not only the BC for training, but the validation as well.
and zero is not a good thing anyway. It may be something, but it's
Sorry, I
not a good.
think
Uh, sure. So I think uh, we can continue. It's fine then.
I don't know if it is happening for me, but the screen got frozen for me. I don't know if it's the same for everybody.
Screen is getting frozen. No, it's
Yeah,
not
it's got now.
frozen.
Now it's okay. Yeah,
Okay. 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 Thank you, Nan. Where are you from?
I'm from Kolkata, sir.
Oh, you're from Kolkata. Okay. Good.
Thank you.
So then should we start the next part? Huh? I think we have answered that. So let us, huh? The same question, I think they have answered. So I think let us move forward. Yeah. So can you share the slides? Huh. Huh. Okay. Okay. So now we talk about CNN and RNN and LSTM. These are actually the building block of deep learning. Okay. So these are building blocks of deep learning. This is where CNN is the first architecture which started this entire deep learning phenomenon. Okay. So what is convolution neural network? Okay. So a convolution neural network is a specialized deep learning architecture designed to process grid structured data, primarily images. So you may be knowing that there was this AlexNet which started this deep learning thing. So deep learning revolution started with vision, with the image. Okay, and then it moved to language. So you will see that these two communities have contributed alternately in taking this deep learning forward. Okay, so initially it was the vision community, then the natural language community came, then then the transformer came, which was a big boost for natural language processing. Again, this transformer architecture then was used for vision. So there has been a very nice healthy debate, healthy competition and healthy contribution from this both communities, and basically these both communities have taken this forward. Okay, so there are other communities which have also contributed, like the graph community has contributed, but I guess these two are the major communities which have taken the deep learning revolution forward. Okay, so convolution network is a specialized deep learning architecture designed to process grid structured data, primarily images. So inspired by the visual cortex, CNN uses learnable filters. So it's a grid structure, and CNN uses learnable filters that slide over the input data to detect spatial patterns like edges, some sort of textures, or some sort of shape. Okay. They achieve translational invariance, meaning a learned feature can be detected regardless of where it appears in the image. So, if an edge appears here in the image, the same edge appears in the next image here it will be able to detect. So there is a translation invariance. Okay. So what are the basic building block of a CNN? There is a local connectivity. Neurons connect to small regions, not the entire unit. So it's a local connectivity. Okay. Then shared weights, same filter applied across all spatial locations. Okay. Then spatial hierarchy. So there is a low level and high level, from low level to high level features through stacked layer. So in the first level, you learn the edges. Okay. Now, when the edges are learned, again in the second level, you see how these edges are connected and see the shape. So this is a stacked layer approach. Okay. This is a stacked layer approach in which way you have a hierarchical level of understanding. Okay. This is a stacked layer approach where you have a hierarchical level of understanding. So see this again. So you have a input, you have a convolution plus ReLU plus pooling. So these are three things. So let me write convolution, ReLU. So in previous thing we were talking about sigmod. Now we talk about ReLU. ReLU is again a non-linear function. So everywhere, if you see the structure, there is a convolution layer, which is, I will show you, it's a convolution layer. Then there is a ReLU and there is a pooling. Okay. So just remember three things: convolution, ReLU, pooling. There are three things which we do. Okay. So slide a small filter. What is convolution doing? Slide a small filter over image to detect local features. Okay. Slide a small feature over image to detect local features like edge, texture, patterns. Okay. Then you have a parameter sharing. This same filter weights reused across spatial locations. So if you have a filter, this filter, which you can see that we have this filter, just concentrate on this filter. This filter will be same and shared across all locations. Okay. Then what happens? It has a fewer parameters, easy to train. Good. Okay. So pooling downsample feature map, and it can do through max pool and average pool. I will talk about this. This is very interesting. Why do we need to downsample? Okay. Why downsample? You can ask this question, that you have a picture with very nice pixels here and suddenly you begin to downsample that. Why? Okay. And then you have a stacking layer, low level edges, mid level shapes, high level objects, and then the class. And this was done, everything started with this AlexNet. Okay. Everything started with this AlexNet. It revolutionized image recognition, and then we have ResNet, VGG, efficient net followed. But AlexNet was the first which made the breakthrough in deep learning. And why? Because AlexNet was an annotated data set. It was a data set created, there was a data set which was annotated, and people could work on this annotated data set. As I have told you last class, the machine learning started with oil, with data, which is the new oil. Okay. So data is important. Annotated data was more important to start the revolution. So now let me again tell it once more. I think I have told, but see, there is a convolution layer, there is a ReLU layer, ReLU activation, and then there is a pooling layer. And then there is a flatten, and there is a fully connected, and a softmax output. So this is something which we will talk later. Okay. But convolution, ReLU, pooling. And again, early layer detects edges and simple patterns. My mid layer, texture, shapes and objects. Deep layer, high level semantic concepts. Okay. So these are the three layers in which way things goes. But now you may again see this. So there is, just put this in your mind: convolution, active pooling, convolution, active pooling, and then a fully connected. Okay, convolution, active pooling. This is how it goes. What is convolution? Again, convolution is about filter. Okay, via dot product. I will come to it. It produces features map. The convolution is the main thing. It produces feature maps capturing spatial patterns. Okay. So, and parameter is like how big would be the strides, the padding, etc. We can talk about this. Okay. So, activation introduce non-linearity. So, you can have fx is equal to max of 0 and x. So, what is fx? It is basically this is what it is, that if it's a negative function, I talked about ReLU last class. If it's negative, then it is 0, and if it is positive, then it is exactly the value. Okay, this is what is ReLU. The pooling layer, it reduces spatial dimensions. Max pooling takes the maximum value in region, provides translation invariance, reduces parameters. Coming to it. Okay. And the fully connected layer, what does it do? It combines all spatial features into a vector, performs final classification regression, often uses dropout for regularization. I think I talked about dropout, so that not all the neurons get activated at some times. Okay, that I talked. So now see this convolution. So you have a filter. So this is a typical filter. So this filter is a 3 cross 3 filter. What this filter is capturing? Let us think carefully what this filter is capturing. So if this filter is put upon here, and you have 1 into minus 1, 0 into minus 2, 1 into minus 1 into minus 1. Okay. And then you have all zeros, and you have this 1 into 1 into 2, 1 into 3, 2 into 2, 1 into 1. Okay. So what is it capturing basically? If, see, these parts, this part is 0. If this part is small, think about this part is small and this part is big, then you will have a bigger value. Okay. If this part is big and this part is small, because see, these two are, one is negative, one is positive, same values. Okay. I'm just thinking about the filter. See, this is minus 1, 1, minus 2, 2, minus 1, 1. So this column and this column is exact opposite. Okay. So, and when you are doing this multiplication, if this part is big and this part is small, then you will get a high value. Okay. And what does this mean? That there may be a line here. Okay. This may mean that there is a line here because you are having a lot of pixels across this straight line. Okay, you are having a lot of pixel across the straight line. So what I'm trying to understand, what I'm trying to make you understand is that this filter captures some essential thing about this value. Okay, about this filter can capture some essential thing about this space. Okay, can capture some essential feature or essential property about this space. And what is the property here it captures? That this side is more heavy than this side. At least it captures this. Okay, this side is more heavy than this side. Let me repeat once more. This is classic image processing. Those who have done classic image processing will be knowing that what is filter doing. So see this filter, this is positive, this is negative, exactly. And if I put this filter upon this and do a dot product, if I do a dot product and that dot product becomes positive, that means this side is more balanced or more weighted than this side. Okay, this side is more weighted than this side, and the more the weight, That means this site is more weighted. So at least from this thing, you are beginning to understand that this site has more values. Okay. You are beginning to understand that this site has more higher pixels. Now you take the next stride. Okay. And if that again happens, say that also happened, then the next stride that also happens. Then you begin to see, this is something connected. You begin to see this is something connected. Fine. So this is how you take this information. Now again, the next time when you put filters upon this, you will say, I have got this connected, and say this was also connected. If this was also connected, that would come perhaps in this line. So if I have 777 here, also 777, something like this, what I can understand, and here 000, think from using this, I get 777 000 777. Okay, what I can understand, that these are spaces, these are places where, which are parts which have uh, input 0 close to 0, but these two places are very strongly, these two places have a lot of pixels, have a lot of positive pixels, and so then you can think, this is something up rectangle perhaps, or these are two parallel lines which are going on. You realize that, these are two parallel lines which go on. So you have first layer, then second layer you go, and you realize that there is a parallel line. First layer, what you realize? You realize that there is something going on here, there may be some straight line here, but in the second layer you begin to realize that these are parallel lines. Okay, so this is very nice in one way. This is extremely nice. What is happening is, you have a first layer filtering, and you get some initial features like edges, or lines. Those features can again be combined. Those features can again be combined. Okay, those features can again be combined, and you get more complex features. Okay, so features can be combined to get complex features. Okay. So this is the beauty of CNN. And just to tell you one thing, that CNN is an architecture which is still used. Okay, in spite of all this transformer etc. coming, CNN is an architecture which really have not gone. Means it has not become obsolete, because it has its utility in various places. Okay, and there are various architectures which are now coming out, which is a hybrid of CNN and transformers. Okay. So, mm, and how do we learn these weights? How do we get these weights? Get these weights. These are the weights which are learned. You learn this weight. So when you are training, basically you are learning these weights. When you are training, you are learning these weights. So let me take a, okay. Next is the pooling. What does pooling do? What does the pooling do? It takes four together perhaps and convert into one. Four together converts into one. Four together converts into one. So you may tell that pooling is not a good thing, because pooling then reduces the, it reduces the mm, reduces the richness of the data. So pooling reduces richness of the data. This can be a common complaint. Okay, and true, because it is reducing, you can say it reduces the richness of data. On the other hand, see, there are So, so there are interesting thing. There was a old concept of skeletonization. Okay, there was a old concept of skeletonization in image processing. Okay, so what is skeletonization doing? See, we are two human beings, perhaps, and how to understand we are two human beings? If we see the skeleton of us, perhaps then it will be sure that these are two human beings. Otherwise, there are too many features which are confusing features, which may not be able, which may not be, which are not confusing features, but which may be too complex for the machine to recognize that these are two human beings. That's why the concept of skeletonization came. So what is that? Keep what is essential. So pooling has many utilities. It keeps what is essential. Okay. Second is it acts as a regularizer. Okay, because there may be noises which is removed. Yeah? It acts as a regularizer. Then see, when you are doing max pooling, 36 comes. Okay, when you are doing max pooling, let us just think max pooling. Okay, when you are doing max pooling, then here 36 is coming. 14 is coming because this is the highest. So then 11 is coming, then 22 is coming. So this gives you a bit of robustness because say this is something capturing animal. Okay, or let me put a car. Okay, so in one picture car may be here, in another picture car may be here. Okay, so when you are training, this sort of small invariance, small translation will get erased when you do this max pooling, and which is a good thing. Okay, you will not be tied by where the car is. Okay, you will more concentrate on the features of the car. And if you remember, I have talked about CNN tries to do this translation invariance, that whether the line is here or the line is here, it shouldn't matter. Okay, so that is what the work of max pooling is. So now once we have this max pooling, you do the flatten, you do the flatten thing, and then after that you have the flatten, and after that you have the fully connected layer. This is the fully connected layer. Okay, fully connected layer, and you have a weights of this fully connected layer, and accordingly you can get weights of each of this class. Okay, so you have a fully connected layer, you have the flattened thing, and then from multiplying this you can actually get the weights of each class, and then you do some softmax thing and you see, oh, the picture is a cat. Okay, so what is happening? How the fully connected layer works? The flattened vector x is multiplied by weight matrix W squared Wx plus b. Each row of W learns which combination of features predict a class. So each row has learned which combination of features is for this class. Okay, so this feature is 0.2, this feature is 0.1, this feature is 0.4, and this feature is 0.1. 0.1. This is how the cat works. Okay, while there are other things which defines a dog, and there are features if they are there, like if the face is flat, that is a negative feature perhaps. So that's why the weights are negative. And there are features which tells whether it is a bird or not. Okay, so this is how you have the fully connected layer and you get the final picture. Okay, so I hope this is clear, and see, you can actually try the PyTorch. Okay, I would say I would recommend you to try PyTorch to do this CNN. So CNN is the first exercise on PyTorch you can do. So we talked about scikit-learn last class. We talked about scikit-learn last class. So let us just a little bit of PyTorch. So PyTorch is a very important. I'm assuming many of you have uh, fiddled with PyTorch a bit, but if not, please go and do it. So there is a neural network building network, like you want linear convolution, RNN, LSTM, GRU, transformer, etc. Then you have the optimizer, that automatic differentiation via torch. Okay, autograd, SGD, Adam. So all sorts of optimization, which I talked last class also about scikit-learn. Same things are there. Then the data loading and pre-processing, like data set, data loader, transform, batching, etc. are there. Then key design principles are there. So all sorts of things, that how to debug, okay, how to have GPU, CPU, whichever seamless switching, all sorts of things are there with this PyTorch. Okay. So, and then you have the model training, you have training loops, loss functions, checkpointing. You know about checkpointing, that you may want to do checkpointing and go back to that checkpoints, because sometimes the training may go haywire. So you again come back, adjust and start and go to a different path. So this is what is called checkpointing. And you have ecosystem use cases like Hugging Face integration. I hope, Miss, please go and see Hugging Face. Many of you may have already seen, but Hugging Face, etc., you should see. Okay. And it is used in CV, NLP, RL, generative AI, etc. Okay. Oh, I forgot to tell that there is this RL community, robotics community, which has also contributed to deep learning in a big way. So the vision community, the NLP community, the robotics community, and also the graph community, which who does many things beyond this. There's a time series community also who does time series. Okay. So just to give you a bit of idea, so here I've just written a little bit that you have a simple CNN, okay, and you have a first convolution layer. You have a first convolution layer where you have the kernel size. How big will be the kernel size? Will you do some padding? So padding is something I didn't tell you, but just let me tell you. So you may want to give a little bit of this thing, because otherwise the filter would have to stop much later. So you do a padding sort of things so that the filter can move. Okay. So this is what you can do. Okay. So these are small tricks, but have very much utility. So all the tricks I would not be able to tell, but it's your task actually to fiddle with them, understand what are each of them working on. Then you have the first convolution network, then you have the second convolution layer, which is again you have the sizes, the kernel size, the padding, etc. Then you have the max pooling layer. Okay. Then you have the max pooling layer, which is which is taking max over 2 cross 2 window and half the H and W. Then you have the ReLU, which is the activation. Okay. So, and then you have the fully connected. So after two poolings, 828 becomes 14 and 14 becomes says 7. And final feature map size is 32 into 7 into 7. Okay, something like that, which is happening. So here just see that convolution you have in out k, that how many, what will be the kernel size and what will be the padding and how many filters will you take for each convolution layers. Okay. So these are all things, means it's difficult for me to exactly teach you things, but these are treasure trove. Huh? You should go, it is easy to understand, but these are things which you should do in PyTorch and give your initial training. Okay. And then you have the forward pass. You first define, then you have the forward pass. Okay. And you have the forward pass and you have the final classification layer. Okay. So I guess I have through this CNN. CNN has huge number of applications. basically in computer vision, it had image classification, object detection, semantic segmentation, facial recognition. Okay. In medical imaging, it is talking about tumor detection, diabetic retinopathy, histopathology, COVID. Okay. And you have also, there is text CNN, but then there was other architecture. Then CNN was not so popular in text, audio classification, video understanding, autonomous. And you will see there was AliNet, which was initial days, very, very long ago. Sometimes when I was a undergrad, so there was AliNet. Then the AlexNet came. VGGNet became very popular. RestNet is one of the most popular, I think, even now. And you have EfficientNet. All sorts of architecture came, and these are landmarks. Okay, so I will just talk about drawbacks and then stop here. That CNN are designed to process fixed size input image and generate fixed size output. So this is a fixed size input and fixed size output. They struggle with variable length sequence if the length sequence is variable, such as sentences in natural language processing or varying length videos. So this is what CNN have the problem. So CNN process data points independently or within a small local window. They cannot inherently capture the temporal relationships. Sorry, what happened? Somebody is controlling. I don't know. Somebody is controlling my machine. They are controlling my machine. Now it is fine. Hmm. Anyway, they cannot inherently capture the temporal relationships or context across time steps. So, time steps it cannot do, sequence it cannot do, making them inefficient for tasks where order matters, like stock forecasting or text generation. So, where order matters, CNN is not a very good. Okay. So, with this, I think I will stop, give a small break. Okay, and ready to take questions also. Yeah, we'll take questions surely. So, can you tell them to unshare? Ah. So, Girish Gupta. So, Girish Gupta has a question. Okay, anyway, I'm telling his question if he's not there. So, how kernels are you unmuted him? But Girish Gupta perhaps is not there. So let me just go. But he has an interesting question. Let me just tell how kernels are developed or configured for feature map development. Please help with the understanding on how do the weights are learned for kernel during training. Okay. So kernels in a neural network are not manually designed in most cases. No, in all cases, they are learned automatically during training. Initially, the kernel values are set randomly. As the model sees the data, it compares its output with the correct answer. So it is the same thing. The weights are there. According to the weights you calculate, and you see that it compares its output with the correct answers, computes an error, and adjusts the kernel value step by step to reduce that error. Over time, these kernels become specialized to detect useful patterns. So if you do this again and again, these kernels become specialized to do certain patterns like edges, texture, and shape, which form the feature maps. So the feature maps are something which has detected edges, which has detected textures or shape. So instead of configuring kernel by hand, we let the learning process optimize them based on data. Okay, so this is something which is interesting. I don't know, Girish Gupta perhaps have gone, so just has just stepped out. So the other question is, I don't see who has given this question, but let me just put it. Why we see the ReLU function, when we see the ReLU function graph, it's mostly linear. Yeah, very interesting question. For z greater than 0, then why it is used for non-linearity? This is a very great question. So yes, ReLU looks linear on the positive side, but key is that it is not linear overall. Okay, it is not linear overall. Anyway, since I have asked this question, I will take it. I see Abhishek Lohit asked this question, but it's fine. For negative inputs, its output is 0. And for positive input, it passes the value through. This creates a bend or break in behavior. So the behavior is not a straight line. And why this matters? When you stack multiple layers with ReLU, this on-off behavior lets different neurons activate for different inputs. As a result, as a result, the network can combine many simple pieces into complex nonlinear patterns, which would not be possible. Okay, but I will also tell you one very interesting thing which happens here. One very interesting which happens because it's a pseudo linear thing. Okay, and what is the gradient of a ReLU? It is 1. Okay, gradient of ReLU is 1. So what happens when you pass back the gradient? You have seen h1. So you have seen h1, you have seen delta, which are working. So you will have ReLU. If you remember, we talked about sigmoid, how sigmoid is doing the back propagation. So if you take ReLU, the back propagation value will be 1, because if you differentiate a ReLU in the positive thing, it is 1. Okay. So that means what? Whatever is the gradient value in the previous layer, that would be just carried forward. And this is very important. And I will talk a little bit in the next thing. This is very important to from stopping vanishing gradient. Okay, so just if you remember our thing, that there is a chain rule. Okay, there is a chain rule which is guiding back propagation. There is a chain rule which is guiding back propagation. Okay, you remember there is a chain rule which is guiding back propagation. Now, if the chain becomes bigger, if the chain begins to become bigger and bigger, there is a possibility that the value would become smaller and smaller. And so the upper layers would have good update, the lower layers would begin to have very less updates. That means the lower layer would not really learn. And ReLU is one function which sees that this doesn't happen too much. Okay, at least the ReLU function checks that the gradient descent for that layer is 1. So it passes. It passes to the lower layer, and the lower layers can also update. So that is a ReLU's interesting function. Okay, we can talk about this in more detail. So I see at least Sharup Kumar. Can you unmute Sharup Kumar and see whether? Sharup Kumar is talking? Huh? Sharup Kumar, are you there?
Yes,
Okay, yeah, please, yeah, you want to ask the question?
yeah, the pooling concept you explained,
Yeah.
sir. I just wanted to understand. It's similar to dimension reduction,
Uh,
like it reduces
see,
dimension reduces the features. How does this differ?
see, I think it is much simpler than dimensional reduction, because in dimensional reduction, what you are trying to do, you are you are packing it. Okay, you are packing the entire information there. Okay, but when you do max pooling, you are not packing. Okay, you are just taking a representative sample. Okay, so yes, pooling is similar to dimensional reduction, not exactly the same. Okay, pooling reduces the spatial size of the data, that is from a large image to a smaller feature map, so that in that sense it reduces dimension, that is fine. However, unlike techniques like PCA, if you think PCA etc., pooling is not trying to find new features or compress information optimality. Pooling is a much simpler thing. Dimensional reduction is a much complex or much sophisticated thing. It simply summarizes local regions, that is taking max or average. If it takes average, there is some way it's taking the entire thing, but max if it is taking, then there is no summarization even. Okay, so pooling is equal to local summarization plus size reduction, while if you think dimensionally reduction is global transformation plus feature extraction. Okay, so these two, philosophy wise it is same, but pooling is a much simpler thing. Okay.
Yeah, understood. Thank you, sir.
Thank you. Okay, so I think any further questions, I think Girish Gupta we have answered. So then can I take a small break? If everybody permits, we can take a small break. Okay, thank you. Thank you. Okay, then we are coming back in 5-10 minutes. 10 minutes. We are coming back in 10 minutes. এটা এটা কি করব? No, where is the PPT? এটা না এটা। No. না, 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 না। Hello? Yeah. It's not coming. Oh, oh. Start. Oh. Okay. So I think we talked about the drawback of CNN and that led to RNN. Okay. So RNN is, again, I have told you that it was driven by the natural language processing community. Okay. The NLP community. So it helped in machine translation, sentiment analysis, named entity recognition, text generation, all sorts of text-based tasks. Okay, and also it has helped in time series thing like speech recognition, music generation, stock price forecasting, anomaly detection in signal. So signal processing sort of things was very good with RNN. Fine. So just to give you at a glance, before we start, that CNN is best for spatial grid data, while RNN is good for sequential temporal data. Okay. Then memory is none. There is no memory. It's just a feed-forward network. But there is a hidden state across timestamps. Okay. And you have convolution and pooling, but you have recurrent weight updates. And there is famous things. Means here there are ResNet, efficient net, but then yeah, means all these are post cursor of RNN. Okay. So RNN, what is sequential data? Let us just delve into it and talk about it one after another. Okay. What is sequential data? Data where order matters. Okay. Each element depends on the previous one. Standard networks treat inputs independently and fail. So here order matters. So like dog bite man and man bite dog, these two are not same thing. Okay. So order matters. So key insight is traditional feed forward networks assume inputs are independent, but in the cat sat on the predicting the next word requires remembering all the previous words. So we need a model with memory. So this is how the RNN, the vanilla RNN is there. So you have a update rule. Sorry. So you have a hidden state HT. Okay. HT is equal to WH T minus 1 and WX into XT. XT is the input. Okay. Plus B. B is the bias which we have again remembered. Okay. So there is this is how the very simple rule of vanilla RNN is there. So just let us go through the equations. So what is the equation? You have HT is equal to tan H. Tan H is another function. So you are seeing all sorts of functions we are using. Okay. Tan H, WH t minus 1, WX, WX xt plus B. And then you have the output computation, which is yt is equal to g of w y into ht. Okay, so you have the ht which you are getting from here, and that is used to have the output computation. And then you have a cross entropy loss. Whatever we are getting at Wt, you are getting because you are actually taking all the inputs. It's not just one input. You are taking all the inputs x1 to x3, and you are getting Wt, and you are basically doing the cross entropy loss. So xt is input, ht is hidden, and these WH, WX, WY are learnable weights, and B is a bias, which is also learnable. Again, so what is happening? Basically, you are having hidden states. You are having hidden states, and this last hidden state and HT is basically a function of WHT minus 1, WX xt plus B, and then you have a nonlinear function tan H. Again, a linear function followed by a nonlinear function. So you will see the same pattern again and again. Okay. And then the final computation layer, which has a function g, which is wy into ht. Okay. So this is how things are. Fine. So what are the issues? So one thing, please try to understand that there is, you have, I would try to understand this thing. So there is only one RNN cell. Huh? So same RNN cell is there. Huh? So it is just unfolded. This is just unfolded over time, but essentially it is the same thing. This is same as this, and this is the same thing, same structure, which is unfolded over time. This is just stacked over time. So unlike CNN, that was a grid. So unlike CNN, that was a grid, the filter was moving like this. Okay, the filter was moving like this. Here there is only one cell which is moving over time. So remember this. Okay. So then what will be the back propagation? So backprop will be through time. So unfold RNN across these time steps, compute gradient at each step, sum gradient and update weights. Okay. So you will try to update weights. Okay. So what is happening? Say if you have t time steps. If you have t time steps, so what will happen? Say you will have DHT dht minus 1. This is what is will happen. So you have ht is equal to some function of ht minus 1. This is what is happening. So ht is equal to w ht minus 1. Just let me write, make it a little bit simpler. Okay. So ht is a function which is tan h w h t minus 1. This is what is it. So that means what is happening, if you are always seeing this dht minus dht minus 1 to see how much update it will come. So this function will continuously come. And so this is same. Okay. This is same every time. Okay. So if this value becomes less than 1, dht minus 1 becomes less than 1, then what will happen? Then what will happen? After say 2, 3 layers, after t becomes say 5, this value will become too small. Okay. So after 2, 3 layers, the value would become too small. Okay. Let me tell you once more. Try to understand. Okay. Now, these are things which will be required again and again. So what is happening? You are back propagating over time. Why? Because there is no space. It's time only. The same structure you are back propagating again and again. Okay. This is what is RNA. Fine. And so then in this back propagation, this value would always be needed. DHT minus 1. Okay. So now if this value is less, very less than 1, it's very less, let's say it's 0.01. So what will happen after say 5 steps? The loss with respect to weight would become very small. The loss with respect to weight will become very small. If loss with respect to weight becomes very small, that means what? That this structure cannot capture the learning 5 step beyond. Okay. So I'm just telling the quick brown fox jumps over the lazy dog. Okay. So this is say 5, 4, 3, 2, 1. Okay. And you are running it for 5 steps. And at that point, DLDW becomes very, very less than 1. Okay. And it is almost 0. Let us write DLDW becomes almost 0. What is the implication? That means this machine cannot capture the influence of words which are 5 step away from the main word. So this machine cannot capture, sorry, cannot capture the influence of words which are 5 steps from the focus word. Okay. Because by that time this value has become very, very close to 0, and we know that what is the weight, how do you uh, update weight? We talked about this in this thing. Okay. Plus DLDW. This is how you update. And if this value becomes very, very close to 0, then there is no update. The weight is not updated. That means the impact of B on T is not captured. Okay. This may be okay, but you may tell, are a 5 step beyond, it is not needed. But I will show you an example why this is needed. Okay. So take this example. Take this example. The dog and cat was fighting and it barked. Very simple thing. Dog and cat was fighting. I don't know whether my handwriting is good or not, but let me write in a better handwriting. The dog and cat was fighting and it barked. And my task is, it is related with whom? This is my task. It is related with dog or cat? Okay. Something like this, I can ask this question. Okay. It is dog or cat. So then ideally it has to have some influence, long influence. These two words are related. These two words are related. Dog and it are related and they are far apart, but they are related. And we need to capture the influence. So, not that for every fifth letter influence is needed, but there are critical sections where this influence has to be captured. And as soon as you have this vanishing gradient problem, these influences will not be able to be captured. That makes the machine not so powerful. So that's why we have a solution in LSTM, long short term memory. Okay, so this is clear. Fine. So when we have this LSTM adds interesting thing. It adds two other things. One is a forget gate, another is a input gate. These are two things it adds. Okay. And then there is a output gate also. So what is the philosophy now? It is philosophy is it tries to understand how much we should forget, how much we should forget, and how much should we remember of the past, and how much should we remember of the past. So see, it is not also uh, good to remember everything of the past. Okay, it is also not good to remember everything of the past, because if you remember everything of the past, you may not be able to move forward. Your learning becomes constrained. Huh? So you have a spousal fight and you remember what happened 10 years back and you begin to fight on that. That is never a good thing. That never helps. Okay. So forgetting past is also very important. Okay. If you forget, you learn. A child forgets crawling when he learns walking. So forgetting is a very important process of learning. Okay. Remember this. So we have to know how much we should forget. Okay. And how much the present input is important. How much of the present input is important. So you are writing two things, how much we should forget and how much the present input is important. That's why you have an input gate. So these are the two things which you take into consideration. Okay. So now let us see how we use these things. Okay. So what has happened? Somehow the machinery has not been able to capture the previous after the previous rounds, the previous pasts, the previous sequences. So that's why we are introducing two more machineries. One is the forget gate, which will remember what is important and forget what is not so important, and the input gate, which will also regulate how the present should be used. Okay, this is the two things which we bring in. Okay. So let us see the key innovation. LSTM adds a conveyor belt state. So it has a cell state, okay, that carries information across many steps with minimal modification, solving the vanishing gradient problem. So what is happening, that in the vanishing gradient thing, we saw that it was DL, 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 and it was forgetting. So we'll see that this cell state will carry information across many steps with minimal modification. So what are there? There is a forget state, decides which information to throw away from the cell state, output values 0 and 1. Okay. 0 is forget all and 1 is keep all, any value between. The input gate decides which new information to store in cell state, works with tanh layer to create new candidate values. Okay. Then cell state updates the old cell state, discard irrelevant info, via forget state. Then add new important input via input get. Decides what the next hidden state should be, filtering the updated cell state through sigmoid 10H. Okay. So there are four things. Just remember forget get. So this is a different sort of things. I will show where the RNN is hidden into LSTM. I will show you that. But just remember forget get, input get. What is forget? It is trying to remember and forget whatever is important. Input get, whatever present is given, whether how much important is that, and everything is a cell state. So there is a state, is a state machine sort of thing. There is a cell state, and that is guided by the output get. Okay. So come to the equations. Okay. So what is forget get doing? Forget get using a sigmoid, and then taking whatever is previous state and the input and getting a value. Okay. This is ft. So we have ft from here. Okay. What is input doing? Input is taking the previous. It is similar to that. It is taking the previous thing, previous hidden state, and the input, and giving a it value. Okay. Input get value. Fine. So these are something like a number. Okay. Let us think get is just a number. Okay. Let us think of a number. I will show you. What is candidate? So candidate is the cell state, means you are telling what should be the cell state, what is the candidate. And you see this is WC HT minus 1 XT plus BC. Okay. So does this ring a bell? What is this? This is basically, if you think carefully, this is basically the RNN function. Not exactly, but it is close to the RNN function. If you just think this through, see this, I'm going back to the, so this is something, no? HT, XT plus B, tan H. Okay. This is what is the RNN function, and cell state is basically taking the input and doing this same thing and getting the RNN function. Okay. This is clear. So this is the RNN function. This is the core. The core RNN is sitting within LSTM. Now you are telling no, the RNN function is not enough. What is now you are telling? That how much of this RNN function you will use is determined by IT, and how much of previous state will you use is determined by FT. So FT tells don't forget CT minus 1 to certain extent. Keep CT minus 1. FT tells, and IT tells take the input to certain extent and you get the CT. So you are now think that this is solving the vanishing gradient, or it is, so that's why it is called long short term memory. So it is now being able to remember important things of past. Okay. So this is what is happening. It is binary of past. And what is output get? Output get is again taking this HT minus 1 XT and BO and producing the output. The hidden state HT is now becoming a function of output state, output get, and the cell state. Okay. So previously HT was this. If you remember, in RNN HT was this, but now you are actually modifying HT and putting HT in various contexts. First, put a cell state and make the cell state stable with previous information. Then you have a output get, which is giving you the output. What should be the output? How should be the output? You are giving that. and based upon that, you are also taking the output and the previous state, the cell state, both together, and then you are telling this is the hidden state. Okay. So the hidden state at every time step is getting all these sorts of correction. So this was the original thing which could have made the hidden state very hidden state. It could not have updated it, but you are doing all these sorts of correction so that large scale or large long context can be still remembered. Okay. So I guess I have given you a good of idea. So this is what is happening. There was the RNN cell, but you have a output gate, input gate, forget gate. Okay. And this is giving you the CT. Okay. This is giving you a CT, and this CT is thought as a conveyor belt because this CT is taking all this input and slowly it is moving forward. Okay. So this is what is long short-term memory. But remember one thing, at the core of long short-term memory is RNN. So essentially what it does, it delays the impact of RNN. It doesn't eliminate the decrease of RNN. It is basically what is it doing? Again, if you think that there is somebody whose health is continuously monitored. Say you have somebody who has some chronic disease, okay, who have diabetes, whose health is continuously monitored. And as soon as it increases, you are getting it down. That is what you are doing to the cell states. Okay. But the core thing, core technology is same. Okay. So means I so let me again just go through this carefully to understand that vanilla RNN suffer from vanishing gradient. They forget information. LSTM solves this with a cell state, a memory highway that runs straight through time with only minor linear interactions, letting gradients flow unchanged over long sequence. That is true. LSTM uses three learnable gates to regulate what to forget, what to store, and what to output. Okay. So again, just to give you idea, I have told this, but forget gate decides what percent of old state to erase, 0 to forget, 1 to keep. Input gate decides which new value to write into cell state. Cell update candidate value to add and getting the cell update CT, and you have a output gate. And output gate, after you get the output gates value, the output gets value and the cell update together give you the new hidden state. Okay. So element wise, what is happening? Add old memory into forget, new info into input. Okay. Fine. So this is how the long short term memory works. So again, forget, input, cell update, output get. Forget, input, cell update, output get. This is how the thing works. So I have again, I may not repeat it, but I tried to write a complete example and present it to you. This will be present with you with your slides. So this slide will be shared. These slides are shared. Huh? These slides will be shared, so you can see it. But just see that you have a forget gate ft is equal to 0.7679. It again is 0.679. So you have a ht 1.5 xt1 ct minus 1.3 and all weights 0.4, all biases 0. Okay. And this is how you get the cell candidature, you get the output gate, you get the cell update. Okay. And you get the hidden state updated. Okay. So ht becomes 0.389 while ht minus 1 was 0.5. So summary, one step LSTM, you have the inputs, you have the forget gate, you have the input and candidate, then you have the new cell updated memory, and you have the updated next hidden state. Okay. So now we have a very interesting tool. We have an interesting tool how to update or how to tackle sequences. So we have understood a very important tool how to sequences the RNA and LSTM combine, and it also did a lot of good work. It also took the thing forward a lot. Okay. So then where we are now standing. So we are standing, we have done the statistical NLP the first day. We have done the statistical NLP, talked about supervised learning, unsupervised learning, etc. Now we have somehow done this second step, not fully finished. We still have to do, but the basic back backbone of this deep learning means now we can classify this as early deep learning and late deep learning. Okay, so CNN RNN architecture which we have done now. Okay, so what are the limitations? The limitations of this R or RNN model is slow computation for longer sequences. The limitation is there is a slow computation for longer sequences and cannot be done in parallel due to time step dependency. So you have to do one step at a time. Huh? You have to do one step at a time. This is a problem. Huh? And then we saw the vanishing gradient problem. I didn't talk about exploding gradient problem, but just to, because I should have talked perhaps, but just to give you an idea, same thing happens. I'm just changing the slide a bit. I hope this doesn't become too jerky to you. So yeah, here I talked about less than 1, but I could have talked about if it is greater than 1. Then what will happen? This value would begin to increase, the weights would begin to increase a lot. Okay. Then that uh, it will begin to hit the mark. Means if the weights becomes too high, if the weights becomes too high, that means what? That means also uh, a small change in input would have a large change in impact. Okay. If you think that Wx, if y is equal to Wx, if W becomes very high, then you change x a little bit, W would, y would change a lot. Okay. Which is good for cryptography. Okay. Which may be good for cryptography, but for normal things, it is not good that you change, say, the to they, or the, or say I to we, say I to we change, and the selection process completely changes. This is not desirable. Okay, so that's why exploding gradient is also a problem. Okay, so and as I've told you, many of these problems are partially solved by LSTM or solved to a lot of extent. I should not take credit out of LSTM, but at the heart of LSTM, the RNN sits. Okay, so then the problem is only delayed a bit. Limited amount of information into hidden state, because these hidden states are packing a lot of informations. The hidden states are packing a lot of information which is not, which is not very good, and history is forgotten after a number of steps. This is again from this the long range dependencies many times are not caught. But see, the long range dependency is caught very well in CNN, because you have a hierarchical thing. Huh? So if you have a gorilla, big gorilla picture, huh? Then first it will identify this part, then it will identify the leg. Okay, then it will identify the other structures, and slowly it will identify the gorilla. Okay, so this is interesting in CNN, that it can capture a lot of long range dependency, but not in the sequential sense. Okay, not in the sequential sense. Fine. So yeah, so let me just summarize what we have learned. Okay, so summarized what we have learned. So see, this is convolution neural network. Okay, and what is happening in convolution neural network? So RN and CNN is a little bit different, but if you think the architecture, a convolution network is ultimately bringing a flattened layer. Okay, A convolution neural network is ultimately bringing a flattened layer, and then with this flattened layer, a fully connected layer works and gives a output. It can be a class 1, class 2. Okay. So there are two parts. This is one part, think carefully, and this is another part. So in the broad architecture, okay, so like there are some small principles I've told you. There is a broad architecture, there is a linear part followed by a non-linear part, and this part you will see repeating again and again, linear part followed by non-linear part. Here there is a very important lesson to be understood, that there is one layer which is bringing in this flattened layer. What is this flattened layer? So this flattened layer, what does this flattened layer represent? If I ask you, what does this flattened layer represent? This flattened layer is representing the picture. It is basically representing the picture in a concentrated way. In a concentrated way. Am I with you that it is representing the picture in a concentrated way? It is representing the features of the picture in a compact way. It is representing the features of the picture in a compact way. Okay, features of the picture in a compact way. Okay, so this is what it is doing. And once you have this compact representation, then you use a fully connected layer and do the needful. So the so this fully connected network, there is no innovation as such. If you think there is a lot of innovation, but I am telling no extra innovation. This is a fully connected classifier. You are just using this classifier. But the innovation lies in how well you represent the picture through this flattened layer. The better you can represent, the better the performance will be. Okay. So the entire deep learning thing is about representation learning. Okay. How do you learn the representation? It is about representation learning. Okay. It is about and I have talked, I told it in last class that see there is a feature extraction. So previously people would do the feature extraction manually. That is that was not the learning of representation, but that was the representing through human experts, representing with the help of human experts. That was what the state of the art before the deep learning came. But here you are actually learning representation. So this is the crux where we should go, and how good the representation we can do will depend, means that would actually guide us, or that will actually drive how good the tasks we can do. Okay. So this is what I will take in and then go to this. So then this is basically, I'm just writing it in a different way. So you are essentially, let me write it in a different way, that you are essentially, if I tell that what you have done in this flattened layer, essentially you have embedded the picture. Okay. Or you have converted the picture. I'm writing it in various ways, so that converted the picture into a semantically rich, semantically rich rich vector. I just want you to understand this thing, huh? That what we are essentially doing, what is the big picture? Okay, what is the 10-feet view? What is the 100-feet view? That is what is very important for you to understand. Okay, so essentially you are converting the picture into a semantically rich vector. This is what you are doing. Okay. So with this in mind, we will have a entire we started an entire new part of means when people begin to I think when people started with CNN they didn't realize this, but after sometimes they begin to realize, and then there is this whole featured learning through embeddings. This is what started. Okay. So a motivating journey from handcrafted statistics to learn dense vector. This is what we will now talk. Okay. So what is happening? So you have raw text. The cat sat on the mat. Okay. Then you have a representation. It is a representation. You have a vector, number, tensor, whatever, and you have a classification generation. This is what is happening. So the representation step is the key bottleneck and the biggest opportunity. It is both a key bottleneck, okay, and a biggest opportunity where innovation can happen. Okay. So now let us think. We will concentrate on vector. So how can we represent vector? We can represent vector as a one-hot vector representation. Okay, assign every word a unique index in a fixed vocabulary. Say now your vocabulary size is 8. Your vocabulary size is 8. So cat is 100 something, king is 00100 something, queen is 0000100 something. So what is the key property? So the first way of representing is a one hot vector. The first way of representing each word is a point in high dimensional space and one is an index I, everything else is 0. So now if it's a vector, that means that we'll have a space. And how big is the dimension of the space? The dimension of the space is the size of the vocabulary. Okay. So one thing is done surely. One thing is surely done, that you have a vector representation. So the first thing is you have a vector representation. No matter how naive it may be, but now we have taken the first step. We have converted cat to a vector, dog to a vector, king to a vector, queen to a vector. Okay. You may not like it. This is very trivial. That is fine, but we have still converted into a vector. So what is the importance of converting to a vector? So if you convert things to a vector, vector is a mathematical operator. So then all sorts of mathematical operations which can be done on vectors can be done on this. Okay, so then that is hugely advantageous. So now once you have converted this, say you do this, the cat is unhappy. Cat is unhappy. So I think there would be one more one here. So cat is happy. So you have cat, these one, then cat is this one, is this one, happy is this one. No, I think there was somehow that a mistake happened. Here it was cat. Huh? The cat is happy. Okay. And the dog ran away. So these are positive and these are negative. Okay. You have two vectors. One is cat is happy, another the dog runs away. Okay, simple. And you can have a linear classifier. So this way you can have a many classifier. This is a negative sentiment you are telling. This is a negative sentiment. And you have a positive sentiment. And you can have a linear classifier, whatever classifier you want to do, and you can have this two class classifier with negative and positive. So this is what is happening when you are converting it into one hot vector, which is good. It's not bad. So what works? Simple, fast, interpretable weights works for what frequency signals. Okay. So if there is what frequency signals, so if there was, see, if there was something like uh, sad, okay, if sad had very high frequency, say 5 times sad has happened, that would immediately be a negative sentiment. So it works for what frequency signals. Okay. What struggles? See, the struggling is happy and joyful are treated as unrelated. Okay. So you cannot, means these two are completely unrelated. So if it, this may have very different impact. Say happy has come twice and joyful has come thrice, vis-a-vis happy has come 5 times. This may have very different impact because the machine cannot understand that happy and joyful are similar words. Okay, and the other thing problem is these are huge vectors, sparse vectors, and they are mostly zero input because if it is the size of a vocabulary which may be 30,000, you have a 30,000 long vector and a sentence may take only a small part of that, the five parts of them may be 1, all others are 0. That is mostly zero input, which is not a very good thing. Okay. So this is good in one way, but brings in new challenges. Fine. So now what are the challenges or what are the limitations? So see that there is no semantic meaning. King and queen are two unrelated dimensions. The dot product is 0. Okay. Even cat is not, cat has nothing to do with kitten. There is a curse of dimensionality because there is a lot of huge dimension, 99% zeros. So it is very difficult to learn. If you have a system which has mostly zeros, okay, which has mostly zeros, then what will happen? So then uh, it has to really understand that, concentrate on one, don't think about the zeros. So that is not so easy, and with small amount of data, the curse of dimensionality remains. Then this sort of things have no word order. Okay, this sort of things have no word order. Dog bites man and man bites dog have identical representation because it is the same way that how many in dog's place, how many in bites place, how many in man's place. And out of vocabulary is very important. New words at test time have no vector. Model is completely by. So why are natural language natural? Because they expand. They are not like regular language. Okay, they are expanding. Okay, they are expanding. They are not limited by the number of words in the dictionary. They are continue. All natural languages expand. Those language which doesn't expand dies. So this is a general linguistic idea. Okay, so these are fundamental pros, and so what we want to keep the vector representation, but we want to have a smarter representation. So we are now going for a smarter representation. So why sparsity breaks similarity? I have told you that sparsity breaks similarity. So one-hot vectors are orthogonal by construction. The model can never discover that cat and kitten are related. We need a representation where similar words are geometrically close. So we want similar words to be geometrically close. This is very important. We need similar words to be geometrically close. Fine. So what is the big idea? The word's meaning is defined by the word. Now how to do this? So now there is a concept of there is a concept of distributional semantics. Okay, so this is a famous quotation. Okay, I know. I hope all of you know the original quotation. You shall know a word by the company it keeps. Okay, so it's following mimicking that you shall know a person by the company he or she keeps. Okay, so this is the original quotation, but this is just changed by J.R. Fitz and told this. So what is the big idea? A word's meaning is defined by the words that frequently appear around it. So a word's meaning is defined by the words that frequently appear around it. So there is a context window look at plus minus k words on either side of the target word. Okay. Build a vector from the distribution of context word across a large corpus. And similar context would have similar meaning and similar vectors. For example, you see banking, if you take two problem turning crisis as banking, unified needs, regulation 2, okay, given its arm a short, something like this. So banking has this context, words will represent banking. So key shift, instead of a word's position in a fixed vocabulary, we encode what words it occur with. So even if a new word comes, okay. So see, native speakers even understands when a new word comes. Even if he or she may not have heard that word, a native speaker can also guess the meaning of a word. Okay, and native speakers also create lot of words. Okay, they also create unknowingly lot of words or some change of their original words, and people easily begins to understand. Oh, this means that. Okay, so instead of, and why that? Because instead of a word's position, we encode what words it co-occur with. Okay. So count co-occurrence, compress and get the dense vector. This is a route to word embeddings. So you are counting co-occurrences, you are compressing, and then you are getting a dense vector. And this is the road to word embedding. Clear? I hope this is even getting clear. Okay. So then what will happen? Distribution semantics. So replace one sparse index with a short dense vector. Every dimension carries meaning. Okay. So a sparse is just one and all others are zeros. But now you have a dense vector. Say you originally had a 500 time 50,000 dimension. You have converted into 300 dimensions. But every value matters. Okay, all values active, and there is a geometry and a meaning, and it is compact and fast because it is just 300 dimensions. It is compact and fast because it is just 300 dimensions. So geometry encodes meaning. So see, this is a very important example, famous examples. Okay, so vector king. Now when you encode this in a dense vector, when you encode this in a dense vector, so vector king minus vector man plus vector woman would give you roughly vector queen. So you have converted words into geometry. You have converted words into geometry and given the words a geometrical meaning. This is completely different. Even if you think from civilization, this is a completely new way of seeing civilization. Okay, you have given the words a different geometric meaning. Like vector Paris minus vector France plus vector Germany will give you vector Berlin, because vector Paris is the mm, capital of France. So take France out of capital and add Germany, you will get Berlin. Okay, very interesting. Cosine similarity, and then cosine similarity of vector cat minus vector kitten is very high. Okay. So this is what dense representation does. And it is all about representation learning. I'm again and again telling how you represent data, how profoundly you can understand data, on that will all the tasks will actually depend. So this is what you are doing. The embedding module learns dense vector from raw data, no handcrafting required. So any object, cat, sentence, image, user profile, embedding module, and I will talk about this word vector thing, and you get dense vector space where these animals clustered together, the royalty clustered together, the places clustered together, and emotions clustered together. It's a three-dimensional, 300 dimensional space, and you begin to see all sorts of clustering happening. So embedding dense low dimensional vector where geometry encodes linguistic meaning. Please remember this, geometry encodes linguistic meaning. So we have converted a very abstract and very nonlinear thing of language into geometry. And that works. Okay, that's why you begin to see all sorts of, means if you use, I guess all of you are using LLMs and get pleasantly surprised. How can it do things so non-trivial, no, not so obvious things? Okay, because it has converted linguistic meanings into geometry and uses the geometric. It can then use the geometry's power to do all sorts of things. Okay, I will now make it more formal. So you have a one hot vector where every NLP pipeline once began. So you can go and see psychic. I thought I will give you a little bit of code, but you can go and see. Scikit-learn has this monad vector thing. So you have this sparse and huge. Okay, where you have 500K and 2.5 GB matrix, no semantics and no relationships. So you can basically create these one hot vectors and you can see that how this similarity are. Okay. And then you go for dense embedding. Okay. So now this dense embedding, what changed? I've told you, but just let me tell you once more that 500K becomes 300 dimensions. Okay, it is like 167 times shorter. All zeros where 500K was almost all zero, it becomes dense floats. It was fixed, means it was not learned, but this was learned. Okay. So you have a three-dimensional dense float learned embedding. This is what you have now. Okay. So this is, and you can again use this PyTorch and you can see how to embed tokens, etc. You can actually use this. But what is the exact algorithms through which we did this? This is the question which you can ask. Okay. And this is the first algorithm, the first famous algorithm is called what to wake. Okay. And there are two parts. One is the scriptgram model and the CBOW model. Okay. So what is scriptgram model doing? Okay. So what is scriptgram model doing? So it is taking the center where the cat sat on the mat. Okay. So it is taking the center word and predicting context words. So it is doing a learning algorithm. Okay. It is doing a learning algorithm. It is putting cat, okay, and trying to predict the context word. Okay. So this is the prediction algorithm it does. And once it does this learning algorithm again and again, then it learns. And this is good for rare words. This is good for rare words because we try to understand how the rare words functions. Okay. The other is CBOW. This is just a opposite way that you input the context was the sat on the mat and you try to see what is this, and somebody says it is cat. Okay. So and if you do this cat, then the system is rewarded, and if you say something else, the pen sat on the mat, then it is punished. So this is good for frequent words because cat may appear many times in the document. So that is there when that context is there. But in rare words, what happens? The data may not be too much. So then you have to give the rare word and then you get the context word. So you can do one of this or you can do a mixture of this to actually train the system. So yeah, I have all these codes which we have written carefully. Huh? The teaching assistant have also helped me with these codes. But you can go back, go down and see these codes, use it, and we'll talk about this. Okay. So what is the problem? So what is the problem? The problem is This is a static embedding and it cannot handle polysemy. What is polysemy? Polysemy means one word having different meanings, like bank. So, bank can be a finance bank, okay, a river bank, okay, fine. So, it can be a finance bank and a river bank. At least two types of bank we know, okay. So, now, both finance bank and river bank will have the same embedding because you are just training the system that way. So, if both finance bank and river bank has same embedding, then what will happen? Any downstream task, this will get confused. Okay. So any downstream task, when I see the term bank, say for a financial institute, I may use a lot of data from river bank to classify something. So the problem is if you cannot handle polysemy, if you cannot handle polysemy, then what will happen? If you cannot handle polysemy, then it will happen that if you cannot handle polysemy, then downstream tasks, the downstream tasks will become downstream tasks will become less accurate. Okay. So this is the problem. Okay. So this is something which has to be caught. So is you can ask, is polysemy too much? Perhaps polysemy is not too much, but polysemy can appear in many ways. Okay, polysemy can appear in many ways. So there can be soft polysemy also, that the same word may have a little bit different meaning in different context. Okay, the same word may have little bit different meaning in different contexts. So it is, you have to capture the context. So you have embedding, but you don't have context sensitive embedding. So you need a context sensitive, or context sensitive is not a right word, context aware embedding. Okay, context aware embedding. So just to tell you one thing again, I am repeating that what you are doing very simple. You are taking a word and seeing the words which are there, and also you may not and seeing the words which are there, or you may see the context and try to predict the word. This is how you go. So this is now tackled. So contextual embedding, same word, different vector, is tackled using Elmo. Elmo is embedding for language models. Okay. So Elmo is language model. So what is it doing? It is using a bi-LSTM. Okay. So it is using a bi-LSTM. Okay. Elmo is using a bi-LSTM. So we have talked about LSTM. What is bi-LSTM? Okay. And so it was not really necessary. So LSTM is going from left to right, but bi-LSTM goes from both left to right and right to left. And what is the rationale behind using bi-LSTM? If you think us also, when we hear, we process hearing the entire sentence. We process each word not by the previous words, but we process each word entire hearing the entire sentence. That's why bi-LSTM is important. Okay. So now if we have this bi-LSTM training, let us think, if we have this bi-LSTM training, then what will happen when I deposit money at the, something will come up, some embedding will come up, that to represent the finance bank. Okay. And she sat on the river bank. This bank would be the river bank. Okay. So this will be a different embedding. So what is happening essentially, I'm not going into more complex. There are three layers of this, but just we are coming to the end of this. If needed, we can talk again later. But just think of this, that when I am when I will run during inference, I deposit money at the bank. This bank will have a different embedding. While C sat on the river bank, this bank will have a different embedding. So every time you run the context, this will produce different embeddings. So that is a contextual embedding or context aware embedding you get through LSTM or by LSTM. So uh, so let us just see what is happening. So see, what to wake is static one fixed vector per node. Okay. Dynamic new vector per sentence. So for every sentence, you have a new vector for this node. Okay. You have a new vector. So if you want to, so then architecture is a shallow lookup table. These are two directional by LSTM. Bank always have the same vector. Bank differs by context. Okay. Context use training time context only, both direction at inference. So the problem is, see, the thing is, mm, this is important. I will tell you, both directions at inference. So the you don't have a pre-compute ones. Okay, you don't have a you have in what to vec, you have a pre-compute vector. So you run the system for all words. Now you have a embedding. Okay, so it's a pre-compute. So for word B there is a embedding, for word H, for word bank there is a embedding, for word light there is a embedding. So you have a pre-compute thing, cache all. So this is very nice, in very good, that once you have run what to wake on all the letter, all the words in English, every word has an embedding, and you don't have to run what to wake after that. You just keep those embedding. But here you have to rerun full LSTM per sentence. Every sentence, if you need a embedding, you have to run it. Okay, but it gives richer embeddings, because it gives the first embedding, the second embedding only considering the left, the third embedding only considering the right. So this type of things, it gives richer embedding, but the embeddings have to be obtained during runtime, while here embeddings are already there in a table, you can just reuse it. So these are the issues. These are the how things are in embedding. So, but this embedding space opens up, and then we will actually come to this famous paper and famous thing, that attention is all what you need. Okay. So I hope all of you have paid attention during the class. So I will now stop the class and we can take some questions, or um, I hope. Okay. So, so there are, so Gaurav Vada, you want to? Okay. So in CNN, after each step of convolution, we we are reducing the richness of data. Shouldn't we be increasing the richness of data? Can you unshare? So see again, this is again there is a famous line that one step forward, one step backwards, two step forward. Okay, so not really. CNNs are not trying to keep all raw richness of the input, but to keep useful information and discard the rest. So see, there is information, there is useful information. Okay, I have told you about skeletonization. After each convolution, especially pooling, some details are reduced and reduced on purpose, but at the same time the network is learning more meaningful and abstract features, because that is what we need. We need not know the entire thing, we need to know, are this guy is working a specs. So that is what, that information you need to know. You need not know how much wrinkles are there here, perhaps you need to know that this person is reading the specs. So that is what is important for you to guess whether this person has, a sight difficulty or not. Okay, so that is what you are doing, useful information. Okay, so abstract features, meaningful and abstract features. So while the raw data size or details may decrease, the quality of representation improves. In fact, many CNNs even increase the number of channels in deeper layer so that they can capture. So we talked about this filter. So there will be many filters, 7 filters, 8 filters, and as you go deeper, you increase the number of channels, because you can actually capture various sorts of deep features through these channels. Okay, so that they can capture richer patterns in more compact and useful way. Okay. Yeah, Anand Sri is there. Anand Sri.
Anant, you have been unmuted. You can speak right now.
Hi, hello, Professor. Thanks for the detailed explanation. So I was just trying to kind of, find out the use cases wherein we can use
Okay.
RNN. As you can
Huh.
say that, with each time step,
So
it
just
kind of,
Anand is coming.
hello, am I audible? Sorry.
Okay, I can wait. Yeah.
Hello, am I
I,
audible?
yeah, sure. You're audible.
Hey, hi. Thanks, Professor, for the detailed explanation. Wanted
Huh.
to understand the use cases of RNN. So, from as you say that it kind of uh, remembers the kind of important bit and kind of uh, uh, removes the unwanted bit with time, right? So, is it
Hmm.
with respect to the audio speech? And can you let us know what are the probably the practical use cases of using RNN in the current world?
Yeah. Sure. So see, RNN do use present and past input in tasks like audio or speech, because those signals evolve over time. So that is what is, if you remember, RNN is taking this sequence, but they are not limited to time-based data. Okay, RNNs are designed to tackle any sequential or ordered data, such as text, time series, or even video frames. So there are a hybrid structure of CNN RNN. Okay, so every frame captured by CNN and then the sequence captured by RNN. Okay, so there has been hybrid. The key idea is not just time but the sequence and dependency between elements. So RNN is extremely good to capture dependency between elements, where the model uses previous information along with current input to make better prediction. So if you remember, I don't know whether you know this hidden Markov models, etc. So RNN is the modern variant of this old, very traditional but very effective models. Okay. In short, RNN works on ordered sequence, whether that order represent time, whatever, time, structure, etc. Okay.
Yeah. Thanks, Professor.
Thank you. Where are you from?
I'm from Pune, sir.
Oh, okay. Great. Okay. Thank you. The next question is from Abhilash Gupta. Abhilash Gupta. Okay. Does forget get to ignore or skip value and cell state is to update current value gets? So again, in a LSTM, the forget get decides what old information from the stale state should be removed or reduced. Again, this is learned. Okay. So these gates values are learned. If you see, if you remember those W's, those are learned from data. Oh, something happened. I'm thrown out. What happened? Okay. So anyway, I think this is fine. The cell state itself is the memory that gets updated, not something that updates the input gate. The cell state is the memory. See H and C. These are both states which are updating and which are keeping a compact information of what is important. Okay. So the cell state itself is a memory, it's a memory that gets updated, not something that updates the input gate. The input gate decides. So input gate is also deciding how much new information from the current input. So you are not taking current input just like itself. So current input is given some weight, but not full weight that anything current has to be taken from current input should be added to the cell state. So forget state, remove old info, input get, add new info, cell state stores and carries the updated memory forward. Okay. The next question is by Prayak Shet.
Prayag, you're unmuted. You can speak right.
Yes. Hi, Professor. Yeah.
Hi.
Thanks for explaining this part. So, when it came to vanishing and exploding gradients, so is it possible for you to explain one example to get more understanding why NNN will fail on this type of scenario and where we have need to bring LSTM?
Why? Yeah.
Why
So,
RNN is failing in this?
RNN. So see again, I told you that okay, we have to go back to the equations then, but so I have taught that in mind. So see what is happening. So there is no, it is not multi-layer. Okay, so RNA. So although in the picture we are showing many layers, in practice it is not multi-layer. It is one gate, one cell, and that is again and again updated. And if the gradient, so the gradient is one gradient, if that gradient is less than 1, so it's not that you have multiple gradient, that gradient is one gradient. If that gradient is less than 1, what is happening? It is basically forgetting. After some times, if you go to 3 steps, 4 steps, you see the multiplication of this gradient becomes very small because you have to follow chain rule. So what is that? What does that mean? That means that longer context would not have any impact in the present context. When you are doing a present context and update, at most the previous context would have some impact. Otherwise, it will have no impact. Okay. But how is that this guy is solving LSTM solving? LSTM is bringing in a cell. This is bringing a cell, and cell is doing this upgrade, doing this back propagation surely, but it is also learning some weights about forget gate. Okay, so that it can bring forward some data which this RNN would not allow it to bring because of this vanishing gradient. So what is happening? RN Again, I have told you that there is a core RNN inside this LSTM. Okay, that core RNN may not be able to get the long dependency, but then we have a extra parameter. So nothing is coming free. Here there is an extra parameter, a forget get parameter. That parameter is remembering. This guy is forgetting, but I am remembering that there was a old data and I have to bring in that old data. So this is essentially the structure. I would request you to go back and see the slide. The slide is very, very well explained. Okay, I guess slide is very well explained. Please see that slide. But the basic idea is there is RNN. If the gradient becomes very small, that means there is no update of weight, that means it is not learning, that means if there is a long context that is not captured in the machinery, this long context here is now captured through an additional machinery, a forget get, which says no, no, you should not forget that, and that forget get brings in this additional machinery. Okay, so this is how things are working there.
No, thanks for that.
Thank you. Okay, so yeah, we have some other question. Aditya Sharma.
Hi. Am I audible?
Yeah, sure, you are doing.
So good afternoon. Thank you for letting me speak up to the team. So I have three questions, sir. So one of them is the weights. Okay. So the question is that when we talk about CNN models, so I did understand the part where you said that the image is translated into matrices. And then, so what I don't understand is how the weights come into play, and then how is it eventually translated to what the context is. So, for example, if there is an image of a cat, I do understand how do we put it into matrices, but how are weights responsible for us to detect what the object is?
So see, if you remember the filter which I have shown, see there was -1, 2, -1, 1, 2, 1. If you remember, if you
Yeah.
see the filter which I showed, there was, so just I don't know whether I can now bring this up, but just to give you, let me try to help you with this. I think you can see. So see this. Just let us have a thought experiment, then you will get it well. Where is the filter? So this filter. So this filter has a specific structure. It is not random. Oh, screen share is off. Okay. Just give me a second. I will share my screen. How to share the screen? Huh? Okay. I will do the screen share. Okay. I think I have understood. Can you see the screen now?
Yes.
Okay. See this structure. Let us just go through this once more. So this is a filter. So these are weights. So -1, -2, 1, 1, 2, 1. And what is this filter doing? This filter is doing a specific task, understanding whether this side is stronger than this side. Okay. This filter has a specific thing. So now you learn the weights. So once you learn the weights, how will the weights behave? The weights means, see, initially you give everything random. Okay, you give everything random weights. And then slowly these filters begin to learn the weights. Why? Because whatever structures are important for the downstream tasks are captured through these filters. So this filter weights gets modified accordingly so that it can capture interesting structure. Think in this way, that there is a downstream task and you have to say whether the sky is red or green, something like that. Okay, and then you have to capture interesting features from this picture to understand whether the sky is green or red. And who will capture this filter can capture. So accordingly the filter weights will be learned so that it get optimized for the task. Okay, so this is how things are working. So you can think that this is a very big inverse problem, that this it has to learn that way. So there are many things which we don't talk now, but say I will give you an interesting question that you are starting with a random weights and then you going to a particular weight. That takes a lot of time. Can we do something better than starting from a random weight and guessing the weights and starting? Okay. So this type of research questions you can really ask, or research or technique. I mean, it's not a research question also, it's an implementation question which you can continuously ask to optimize things. Okay.
Okay. So my second question is related to language.
Hmm.
So you said that we give each word a geometric uh, meaning so that we
Hmm.
can form sentences, right? So how
Hmm.
is grammar translated? So what I'm trying to ask here is, let's say there is a sentence which is cat sat on the mat,
Hmm.
and then there is a sentence which is mat is being used by the cat.
Hmm.
So both of them have the same context. How do we translate the grammar here with the weights, with the geometry?
No, see, yeah, it's a means again many things we don't understand. Huh? This how LLM. Although we have created LLMs, we don't understand. Huh? So just to give you a basic idea is that all these sentences means there is all these words having have some contextual embeddings. That means they are somewhere a vector, somewhere a vector, and that vector space has some semantic meaning. Okay, so in grammar, so you are not learning grammar per se. Huh? You see, you have to think in this way that where are you from?
I'm from Jaipur, Rajasthan.
You are from Jaipur, and what is your mother tongue?
It's Hindi.
Hindi. So how did you learn Hindi? Did you learn grammar to learn Hindi?
It was learning based, obviously, like
And it was learning.
experience.
So
Yeah.
what happened? If you think carefully, what happened? Somehow the vector space in your brain has done some sort of clustering, that this is how I have to speak present tense, this is how I have to speak past tense. Okay, this came very means we tell very naturally, but there was some sort of clustering in your vector space, means in your brain vector space. Essentially that is it what doing in very high dimensional space. It is doing clustering. This is the right sort of grammar, this is the wrong sort of grammar. They are beginning to cluster in this very high dimensional space. That is what it is learning again, and that is amazing. That is one thing is amazing. We really don't know how good, how they are learning so well. But one thing, this means we'll talk about this transformer architecture. So the transformer architecture, huge elastic capacity, more data they learn more, so that is also very important. See, this is a little bit unhuman, because in a human, if you have teach your try to teach your son and give five tutors, seven tutors, 10 tutors, he will not learn more. Okay, but these things learns more, and many things are not really understood now. Okay.
Sir, I have last question. So
Yeah,
this
sure.
question is program based, not the content based. So
Mm.
the question is that so I do find myself being confused about the mathematics when we talk about the functions, the equations. I find myself confused. So what I wanted to know is how important is going to be it? How important is it going to be for me to remember the mathematics behind all of the things that we have talked about to progress in this
See,
program?
again, see, there is two things. One is the more you remember, the better. But the more important thing is that whether you are getting 100 feet view, a 50 feet view, a 30 feet view, that is important. That whether you are understanding the intuition, what is happening, because the field is moving very fast. Huh? We have a 8 months course. Okay, you will see by the time of 8 months, many things we teach may look old. Huh? That may even happen. So you have to have a very good intuition. That is very important. That what is exactly happening. The detailed mathematics is not so important. Okay, detailed mathematics we teach because we try to give you intuition. It is not very important later. But whether you are seeing this, why do you want to? Why Why do we need to do mathematics and we are putting exact examples here? Because we want, because that would help you to get, means, have this intuition, develop this intuition. And once you develop the intuitions, everything else will be very simple, because now you know how to code. Coding is also becoming very commoditized. You can use many tools to do coding, etc. So those things would become very commoditized, but the intuition will stay with you. The question is, at this present point, it is important to understand the problem, define the problem. If you think the present way how things moving, and that wouldn't come by mere doing some programming. That would come if you develop good intuition, appreciate the system. You have to appreciate the system in its way. Okay. And some mathematics would need it, but that is not something which is stable. Means anyway, as a teacher, I will begin to give a lot of gyan on this. Okay. So I guess I have answered your question well. Okay.
Yes, excellent explanation, sir. Thank you.
Thank you. Thank you. Okay. Do we have any further question or? Okay, so then I guess we have a very good session. Okay, and thank you all for joining this session. We will continue. Okay, uh, we have just started, so there is a long 8 months going on. So we'll continue. Thank you. Thank you very much. Hello. Can you hear me? Yeah. Any further question? Any further things we can?
Uh, Prayas, you've been unmuted. You can speak.
Yeah. Hi, Professor. Thank you for being here. Am I audible now? Hello.
Yeah, yeah, yeah. Audible. Yeah.
Okay. So, Professor, for CNN, you mentioned that we are having the image processing. For RNN, you mentioned that the time series data is a big advantage for these architecturals. Now, you also gave us one example about Gorilla in RNN session. So, and you
No,
mentioned
I
that.
gave it the CNN session. Yeah, not RNN.
Okay, okay.
So
Because I
I
remember.
told, actually, sorry if I told, when I was talking about RNN, I
Mhm.
told that CNN is still very powerful, because CNN has this, CNN can still capture this long range things, that it can capture the gorilla, means it can still understand gorilla even if its head is very far away from its leg, perhaps. So that was the idea I told that. So that's why CNN has a lot of, even lot of, see, RNN has been mostly replaced by transformer architecture, but CNN is still has its niche. That's what I was telling.
Okay, okay. So basically, for stock analysis and time series data, we use RNN, and right now we are using transformers now.
Yeah, we have begun to use transformers, so transformer
Okay.
architectures.
And sir, one more thing, please. When are we going to see live demos of the practical sessions? Because these theories, they are a bit like a heavy thing to digest for me. I'm not very. I know we have been discussing a lot of mathematical concepts, but still I'm struggling a lot on these points.
Yeah, I see, Prag, one thing I will say that it is good to struggle in the first days, huh? So that you can also go back and study and get things done. So we'll have a lot of demos. So that will come, and this is a 8 months program. We'll have a lot of demo and lot of things going on. And so here, the entire department is gearing and trying to help the team. So there will be a lot of demo, but I'm still telling that you need to build, as I told the previous person, you need to build intuition. You need to understand, and you need to get through, because a demo is a demo, but you have to get through the basic structure. Otherwise it will, your marketability will not come. Means we have been teaching many people many years. This is more important. If you have to have a edge, you have to get through, and don't get too much afraid or too much bothered about the math. Just try to understand the concept, and you can understand the concept even beyond math. Means, and I'm doing very simple math, not means I don't know, you can give me things, but I'm not doing very simple math.
Yeah, maths is fine, but it's almost like 13 years to me in the
I
in the IT
understand.
industry, and
I
I've
understand the
lost the
point.
concepts a lot. So yeah.
I understand the point. I understand that. So we are going slow. We'll repeat again. But I want you to understand the concept.
Right.
Don't take that shortcut. Okay. This would
Right.
means you are spending your weekend, you are spending your money. So don't go for shortcut. Okay. That is, as a teacher, I feel I can give you this small advice.
Sure, sir. Thank you so much. Thank you.
Thank you. Where are you from?
I'm from Noida, sir.
You are from Noida.
Yes, sir.
Oh, okay.
Yeah. I don't see much of the participants from Noida here, but yeah.
Okay.
Sure. Thank you.
Thank you. Okay. Anybody else?
Dear learners, I will be unmuting some of you and you can ask your questions. Thank you. Ruby, you can speak. You're been unmuted. Ruby, you can speak.
See, one,
Devashish, I'm going to unmute yourself. Devashish, you're been unmuted. You can speak.
Hello. 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 Am I audible? Hello.
hello. Yeah. Yeah, we can hear you.
Yeah. Hi, sir. Thank you for
Hello.
a deep and very informative session. I have a couple of questions. One is, can we go back to one of the PPT slide where you were explaining how we have used the four by four matrices and converted it to 2 by 2 using the max pooling? I have a very conceptual doubt over that. If we can touch base on that, sir.
Yeah. I saw. Interestingly, that slide is on the front of me. Okay, I'll just share that. Just give me a second. Can you see it? Yeah.
Yeah. So I have only one doubt over this, because this is converting a 4 by 4 to 2 by 2 matrices using the
Huh.
max pooling concept, and here we are using max pooling, not the average. So why we are beginning with the, like, if it is 2 by 2, why we are beginning with the first row and first column itself? if we use the padding, and why not it is the other four rows and columns? What I mean is, why it is not 20, 36, 8 and 14? Why it is 12, 18, 20 and 36? Like
See, this
how
is
we
just
can.
a cartoon. This is just a picture I have shown. So if you do some padding, you can do that. Means there is no big deal here. But and those will not be a very big problem because you are seeing it is a 4x4, but think it is a very big picture. Huh.
Correct.
If you think of a very big picture, if you do a padding here, padding there, it hardly matters.
Correct. So that, hence it was a conceptual doubt. Like it will move based on the stride, correct?
It is.
It will move based on the stride, correct? Like whether my
Yeah.
padding stride is
No,
40.
but pooling is not based on slides. Pooling is not slide. Pooling is not stride. The masking is based on stride.
Hmm.
Because pooling is you are converting a 4x4 into a 2x2 into 1 or a 4x4 into 2, something like that. Pooling has no stride.
Okay. Okay. Like,
Okay.
uh, yeah, got it. Got it. The other questions are already answered. So thank you so much.
Thank you. Thank you. Where are you from?
So basically, I'm from Kolkata, but currently residing in Mumbai.
Oh, okay. Okay. Good.
Yeah. Thank you.
Thank
Speak. Arvajito, you have been updated. Please please.
Yeah, I cannot hear because there is too much noise.
Anyway, so that's great.
Cannot hear. There is some noise. Oh, okay. So I can mute. Then I think it will come.
Should we be unmuted?
Yeah, hello. Am I audible, sir?
Yeah, you're audible. Please go ahead. Please, please
So
tell your
thank you for
name
the
and
session, sir.
huh?
Okay.
Yeah,
Myself, Shubhi. I have a question regarding whenever you have been speaking about these slides, like the slide which is open in you, there are matrices, sir. I mean, I have a little bit idea that these numbers reflect that how much data is there in that particular bit and byte. Am I correct in that understanding, or can you explain that what does
what is
why the
what is 36?
yes, what is 36?
Yeah, means
Yes.
it see it is coming from the don't know what's happening. I cannot change my slide. Ah. So see this that yeah, so somehow I cannot use my slide. এই তো এখানে যেতে পারছে না। স্টপ শেয়ারিং করে আবার শেয়ার করে অপশন করে আবার শেয়ার করি শেয়ার শেয়ার এই স্লাইডটা তো এটা তো এবং চেঞ্জ করে ফুল স্ক্রিন করে ও আচ্ছা দেখ মেসেজ আসছে নাকি কি আসছে I cannot change. Somebody is controlling my slide. Is that good? Anyway, let me just I somehow I cannot change my slides. What is happening? I don't know. Oh, yeah. Just give me a second. My slide is I cannot change my slide. But what is happening? My slides cannot be changed. Huh? No, what is Zoom's problem? I don't. But the Discord. No. Message আসছে নাকি? এটা কি আছে? talking is. হ্যাঁ, তো হচ্ছে না, হচ্ছে। এখন এই স্লাইড কিছু করা আছে। Yeah, but slide is also, I cannot use the slides. না, স্লাইডটাই তো ইউজ করা আছে। Yeah, but slide, yeah, I can. Huh? Yeah, I'm understanding, but the slide is not changing. Anyway, so just, are you there?
Yes, sir, I'm here.
Yeah, I'm sorry, something is happening. So you can change the slide? Okay. So see, there is a pooling layer where you have this 36, 18, 12, 20. You are right. It is, how is it coming? So go to the previous slide. So previous slide, how is 7 coming? 7 is somehow capturing the 7 is somehow capturing the weights of that neighborhood. Is capturing the weights of a neighborhood in a particular way. 7 is somehow capturing the weights of the neighborhood in a particular way. So 36, you're right, when it is the value 36, that means that in some layer there is some weights which have got aggregated into 36. So this is what is where. So if I physically begin to think, go down, let us physically begin to think, how will I differentiate between 36, 20, 18, 12? So I begin to think that each of these four quarters, 4 cells represent one concept. Okay, each of these 4 cells represent one concept, and that may be the concept of a cat. Okay, that may be the concept of a cat, and this 36 best represent that concept. Okay, others represent it in a more diffused way, and 36 represent best. So I am doing max pooling and taking 36. Okay. So
Okay, sir.
it's a bit conceptual. It's a bit conceptual. If you tell me that, can you show me? I cannot show you, but this is a bit conceptual, and but it works in that way. That if you so there are actually other papers like GradCam is a paper which sees that which part of the means if I am see there is interesting experiments. Say there is dogs and huskies. This is a typical example. Dogs and huskies, and husky, husky looks like wolves. Okay, husky dog. Have you seen husky dogs? So they look
Yes.
like wolves. Okay, so huskies and wolf, and you gave it to differentiate, and this person, this CNN differentiates huskies and wolves only if huskies have a white background and wolf have a green background. So it is not learning huskies or wolf, but it is learning the background. Okay, so that also happens. That's why there are works like GradCam which not only says okay this is husky or this is wolf, they back propagate and tries to find out which area has been important in deciding this class. which area has been important in deciding this class. So bottom line is, all these concepts, all these weights surely generate some concepts or surely represent some concepts, and max pooling just tries to bring out the best concept, but these are again best case effort. Okay, there are cases where you see that it doesn't work. Okay.
Thank you, sir. Sir, one more question I have. So,
Yeah, sure.
after CNN, we moved on to RNN, and as you said, that RNN is more suitable for the sequential data. When we have a data which is in the form of sequence, but we are expecting a little bit of miss parts in that. So, should we not use RNN, or can we enhance the data, or can we just use a segment of that data which is in sequence to use RNN?
Now you tell sequence, there is sequence and there is some missing things. Are you telling
Yes,
me?
yes. Yes,
Yeah, so
yes.
that is if there are some missing parts, but there will be missing. So there is a lot of data on which you are working. Okay. So I will try to frame your question in a little bit better way. That said, you are taking time series data where some of the data points are missing. Okay. This is what you are thinking. So now
Yeah.
what to do? Will RNN work? Or you have to reconstruct something? So it will work still, because it will uh, learn and it will know how to impute those data sets, because it is going with, it is using a lot of data sets. So from other data points, it will understand, oh, there is some imputation needed, and you put that data. So RNN in principle will learn, even if there is a little bit of corruption or little bit of missing data. RNN still learns well. Okay.
Okay, got it.
Okay.
Thank you, sir.
Where are you from?
Gurgaon.
Oh, okay. So somebody was from Noida. Yeah. Okay. Okay. Any further things, or we close it?
Sir, I have one question. Can I ask now?
Yeah, absolutely. Please.
Sir, good morning, good afternoon, sir. Sir, your session is very, looks to be very good because I have been seeing these topics almost 15 years ago. But things are like some of the slides which I really to understand the deeper level, like complex data, which you have taken some of the examples when some of the base processing words like a cat, dog, and a horse, and some of the statements which have taken. So those complex data, when we try to push into a real scenarios, maybe it could be a processing of a circular data set.
So yeah, you are telling this classic example of SVM. Can SVM is a linear classifier, and
Yes,
can it
yes,
do a
yes, sir.
circular? I
Yes,
understand.
yes, sir.
So
Yes, sir.
CNN works very well there.
Okay, sir. So when we do this data on the circular processing, so does any computing time over calculates for this processing data, or maybe we do some additional algorithm needs to be created to reduce the complexity of circular processing of the data, or maybe
No additional thing is needed, because CNN is again, I have told you that it captures first the cycle, then it captures the entire thing. So this is a very good thing. This CNN can, so this you have done some old SVM, and this was a classic example. Very good for bringing this up. That's happened when you have people with experience, they can bring examples which we forget. But this particular circle thing, CNN will do very good, because as I was telling, that first it captures the lower level structures, and then it combines these lower level structures, and then captures the higher level structures. That was the gorilla example. First is
yes, sir. Yes, sir. You have drawn in a picture also that it will be at the lower level. It will be having some water, and it will be go into some absolute phase. From there, it will be go into top. Right, sir. Sir, but when we go the step by step from bottom to the top, do we work any optimization on this, or do we have any scope to increase the cycle time or maybe the cycle run?
See, it is about how many layers you put.
Okay, the
So there are
layers
two
means
things.
about
How many
layers means
layers
okay,
and
okay,
for how many filters you put. Okay.
okay,
You
okay,
can
sir.
put a lot of filters and lot of layers. Okay.
Okay, sir. Thank you, sir. Thanks.
Thank you. Where are you from?
I'm from Hyderabad, sir.
Hyderabad. Okay. Okay. So people from all over the place. Okay, I think everybody wants to go to lunch now. So let us stop. Let us close this. Hope everybody has good feedback and good thing to do, work to do for the week. Okay. Okay. Bye.
Thank you, Manas, for joining the session. We are ending the session right. Thank you.
ఇంత కలిసి రావడం ఇంత కలిసి రావడం ఉంటారు దీంట్లో సాధ్యం